science talks today, and we have a little bit of time for discussion at the end, and then we're going to finish up around 4:30 Mountain Time. And tomorrow we start at 8:30. So tomorrow we're going to do the morning tomorrow. So we were trying to accommodate speakers in multiple time zones, including some in Asia. So that's part of the reason for the different times on the different days. So thanks everyone for joining us. So I'm Marika Holland. I'm the co-chair for the Polar Climate Working Group, along with Hansi Singh from the University of Victoria. And Dave Bailey is the liaison for the Polar Climate Working Group. And we also have Bill Lipscomb and Jan Lennertz, who are the co-chairs of the Land Ice Working Group, and Gunter Legge, who's the liaison for that group. So we're going to be kind of alternatively running the meeting throughout the day. Well, today it's going to be polar, and then the next couple of days we're going to be splitting between polar and land ice. So without further ado, I'm going to start out by giving some updates on the working group. And just so all the speakers in the session know, basically you're just going to be sharing your screen yourself. So hopefully that was clear. So I will go ahead and get started with the Polar Climate Working Group update. Sorry for the delay. Hopefully this comes up. There we go. Okay, so basically Dave and myself are going to give an update that includes the plans for CESM3 and also some thoughts on post CESM3, some new community simulations that we want to make sure people are aware of and start to use, and also some updates on CEIS consortium activities.
We're seeing only a single white strip from you.
Oh. Okay. That's weird. Let me try that again. Sorry about that. I don't know what.
Much better.
You can see it.
Oh, actually, it was in full screen and then it popped out of full screen.
Is that full screen? Yep. Okay.
Great.
Okay. Great. Okay, so basically plans for CESM3 and beyond, new community simulations, and CEIS consortium updates. Okay, so in terms of CESM3, the plan is that all the component models, so sea ice, land ice, atmosphere, ocean, et cetera, will be ready by summer 2023. And then we'll start coupling them together and assessing the coupled climate simulation. And of course, there will be a lot of work after that to get a good coupled climate simulation. In terms of the sea ice, the plan is that we'll be using CEIS 6 model physics. So new model physics that's available in CEIS 6, including the improved snow physics, the land fast ice parameterization, the flow size distribution from Letty Roach and colleagues, and hopefully some improved wave ice interactions and coupling to the newer version of the Wave Watch model. The things in orange here are some of the things that are less certain, and the green things are things that are more certain. We're also adding better ice-ocean freshwater coupling, so Dave is working on that. There's efforts to add a Ccd capability within CEIS, and Dave will be talking about that at the end of this presentation. And we also would love to make use of the sea ice biogeochemistry within the CEIS model and coupling that to the ocean. That's in orange here, however, because we don't really have the resources in-house to do this. So if there's anyone out there in the community that is interested in this problem, we'd love to chat with you about that. In terms of post-CESM3, there's lots of plans for improvements to the model, including parameterizations of subgrid scale snow heterogeneity, improvements to numerous aspects of the albedo and the parameterization of albedo in the model, improvements to the pond parameterization in the model. And if there's other things, again, planned in the community, we'd love to hear about them. I also did want to bring up the Dart data assimilation capability. So as some of you know and have been working with and working on, there is a working interface between CEIS and Dart that's available, and there's lots of great research activities ongoing with that. And the Dart group has reached out to us and is interested in whether there are additional cryospheric data sets that would be useful to support things like ISAT2, other satellite data products. So we'd love to hear people's thoughts on that. And so we are planning to return to some of these topics during the discussion session, very briefly at the end of today if there's time, but more in depth tomorrow. We have a longer period for discussion, and these will be some of the discussion topics we'd like to address. Okay, I also wanted to make sure people were aware of these new community simulations that have been performed. So basically, we've done CESM2 simulations, but with forcing that's comparable to what was used in the CMIP5 CESM1 lens simulations. So the purpose of this is that there's many studies that have documented differences between CESM1 and CESM2. And CESM2 is a quite different model than CESM1. But at least for the historical and future forcing simulations, they were also run with different forcings. And this is probably more surprising in terms of the historical forcing. So basically, we wanted simulations that would enable us to disentangle the role of model structure versus model forcing on the simulation differences between CESM1 and CESM2. So that's the purpose of these simulations. Basically, we have a 500-year pre-industrial control run that actually has different forcing between the CESM1 and CESM2. We then ran a single ensemble member branched at 1850 to 1920, and then we have an additional 9 members branched at 1920 and run through the 21st century. And so they have a per limb anomaly at the beginning of 1920. So this design is very similar to what was done in the CESM1 large ensemble. And it has, again, forcing that's comparable to what was used in the CESM1 large ensemble, including for the historical and for the scenario. And so for the scenario, it uses the RCP 8.5 forcing. So just a couple brief examples showing the value of these runs and how they allow us to disentangle the role of model structure versus model forcing. So this shows global surface air temperature changes as a function of time over the 20th and into the through the 21st century here. And you can see the CESM blue, CESM2 in blue, CESM1 in green, and these CESM2 CMIP5 simulations in black. So basically, we see that CESM2 has less 21st century warming than CESM1 in terms of the large ensemble results. And we can then attribute those differences to the role of model structure, shown in black here, and the role of model forcing, shown in blue. And so basically, you can see that this reduced warming in CESM2 large ensemble is due primarily to forcing, or completely to forcing, and it's counteracted a little bit by the model structural differences. So maybe this isn't too surprising, given that they actually use different scenario forcings for the 21st century. But we see things that are more surprising when we look more regionally. So what I'm showing here is the zonal surface air temperature change. And now I'm showing the change just over the 100 years into the 21st century. So basically over the historical period. And what you can see here, so this shows the zonal, or the air temperature change zonally averaged for the different simulations. And very briefly, what this shows is that CESM2 large ensemble in the light blue warms more in the northern hemisphere than the CESM1 large ensemble. And over the historical period, we can see that the model forcing and model structure actually counteract each other. So model forcing drives more warming in the Arctic in CESM2, but less warming in the Southern Hemisphere, whereas the model structure drives less warming in the Arctic and more warming in the tropics. And some of this forcing change is associated with biomass burning and those emissions that Patricia Duret-Pentenier has highlighted in previous talks given in the Polar Climate Working Group. If we look further into the future, we actually see something quite different. So now we see that the CESM2 warms less in the Northern Hemisphere, and particularly in the Arctic. So this is different than what you see just over the historical period. What we find is the forcing drives less warming everywhere in CESM2. Again, this is associated in part with the difference in the scenario. And model structure looks quite similar as it did to the historical warming. So it drives less Arctic warming, but more tropical warming in CESM2. So we're using these simulations to disentangle these kind of aspects of the changing climate and what's responsible for them. And we'd love it if other people are using these simulations as well. So we do have a website available where there's more information on the runs. We're collecting information on studies that people are planning to do. So please email myself or Cecile Hannay if you're planning to use these simulations, and we'll add those to the website. And also the runs are available on the campaign storage in this directory. We are working on an overview paper, so I'm leading that. That'll document the runs and sort of some high profile sort of climate results. This is, again, I'm leading this with input from a number of different working groups, but we'd love it if these simulations are used more broadly. So please think about how they might be useful for your research. Okay, so now I'm going to turn it over to Dave, and he can just tell me when to advance the slides.
Yeah, thanks. So I guess this is the other hat I wear, is the representative to the CEIS Consortium, which is, those of you who might not be familiar, it's a multi-agency group of people who are working together to keep the CEIS sea ice model going forward. We've had several releases up to this point, and part of what we did was we split out the vertical thermodynamics into a package known as IcePack. We have new online documentation, thanks mostly to Alice DeVivier. Basically what I wanted to say here is that we've just released the latest versions of CEIS and IcePack, and these include updates to the EVP and VP solvers, as well as some forcing updates. And I'll talk a little bit about that on the next slide, but also the standalone drivers, so CEIS can still be used in a standalone mode, include a number of forcing options, including the Japanese reanalysis product. So work is currently underway for Ccd grids, and that's what I'd like to go into on the next slide. So what is the Ccd grid? I think that most of you are familiar with the B grid idea, where at the center, all the scalar variables like temperature, the ice thickness, etc. That's where they always sit, is at the center of the grid cells. But on a B grid, the U and V of the velocity components go in the upper right corner. You can see it labeled here. So what a C grid does is it adds the normal components on the faces, or it moves the velocities from the corners to the faces. And the C grid describes only the normal components. So the U on the east side and the V on the north side. However, we started work in this in-person code camp back in November on a sort of combined CD grid. And what the D grid gives you is it also gives you the tangential components. And so there's some advantages to that with Coriolis and so forth. But you can see most of the information here. I think the thing that we're still thinking about is we've been doing this in a quadrilateral grid sort of sense, but Marika, if you hit forward, there should be a second. Yeah. So what happens when you get to some sort of unstructured grid or whatever, and it becomes more complicated. You can see here, this is the normal velocities on a hexagonal grid. And so then you got to be thinking about more generalized ways to do this. But that's sort of down the line for us, and the people working on E3SM have sort of already been dealing with this. So, so then one of the features on the next slide, please, that we're adding are some new idealized test domains. And so on the left is a simple sort of channel, and hopefully none of you are red-green colorblind, but the white areas are land, the blue areas are open ocean, and then the red area is sea ice covered. And so it's maybe a new flag for the CESM Consortium, but anyway, it's one of our nice new simplified domains. And the idea is that we've added a lot of forcing where we can have just the winds at a constant speed from any direction or whatever. And we can have this configuration of a simple channel, or on the right, maybe like a more complicated design where we add in some islands. And in particular, we add in some 1 grid point wide channels, which is why one of the motivations to have a C grid is that you can then simulate these 1 grid point wide channels. So then the next slide. So we're almost there. So on the left is a B grid solution. On the right is a C grid solution for a channel flow that goes into a wall. And you can see here, there's a lot of noise in this C grid solution. And so we're still sort of trying to root out whether it's something fundamental in the staggering or if there's still a bug in the implementation. But nonetheless, we have it running, and it will run for several days. And in fact, for several years, as I'll show on the next slide. We did these, we did these global Gx3 simulations with these B, C, and CD grid variants. And you can see that it generally physically looks pretty good in March on the left, September on the right. But what we are seeing is that the ice is much, much thicker on the C and the CD grid solutions, especially along sort of Greenland, Northern Canada. And we're still trying to sort this out. As I said, it's not clear yet if it's something just inherent in the staggering or if there's potentially still a bug in the code. But otherwise, we're making good progress, and the hope is to have this released in the CESM code in the next 3 months or so. With that, I'll end there.
Great, thanks, Dave. So I'm going to stop sharing, but and I know we're running behind because I have problems with my Zoom, but I think people are putting questions in the chat. So why don't we do that? And you know, Dave and I will try to address the questions in the chat because I'd like to make sure we don't shortchange the speakers in the session. Okay, so next up, we have David Clemens-Sewell, who's going to be discussing snow redistribution on Hedong sea ice. So you should just be able to share your screen, hopefully, David, and great.
All right, can you all see that?
Looks good.
Awesome, thank you. Yeah, so thanks everyone, and thanks to Marika and Dave and Hansi for organizing. So today I'd like to just give kind of a work in progress update, if you will, on some ongoing work that we're doing looking at the impact of snow redistribution onto young sea ice in a subgrid scale sense. And the importance of that in CESM too. And the first part of this talk I'm going to show some motivation from some submitted work that we've done. I'll have to go through that kind of quickly just to try to stay on time, but I do have a preprint of that if anyone has questions, or please feel free to email me later on. So, okay, so again, this is an agenda briefly where we'll go in this talk. I'll start with the motivation from some observational work and some offline analysis we've done. Then I'll describe the snow redistribution scheme that we're using to implement snow redistribution onto young ice in a coupled climate model. And finally, I'll talk mostly about our kind of preliminary results from a 50-year pre-industrial control run. But to begin with, just want to introduce to everyone the idea that young Arctic sea ice preferentially accumulates wind-blown snow from wind-blown snow redistribution. This happens due to actually a number of different mechanisms that are particular to young Arctic sea ice, such as frost flowers or the sticky brine skim. And this has been observed for decades, actually, by observers. We had a great opportunity on the Mosaic expedition to observe this process in situ. So we observed a number of different young ice areas and found a range of preferential accumulation from about 2.5 to about 8 centimeters. And what I mean by preferential accumulation is that this young ice that we observed on the Mosaic expedition was accumulating these several centimeters of snow, even when we were having little to no net precipitation coming down. And so the mature ice was actually accumulating very little snow. This is snow primarily that's redistributing off mature ice onto the young ice. As I said, for Mosaic, we saw a range of about 2.5 to 8 centimeters. We compared this with some literature results going back decades and found a similar range of about 2 to 10 centimeters in the literature. So we think that this process is relatively universal to young Arctic sea ice at different times and in different locations. And so to investigate, how important could this be when thinking about the heat flux in Arctic sea ice, we developed this offline snow redistribution scheme, where effectively what we did is we took climate model output from CESM2, and in the output, we just redistributed the snow from the thick ice onto the thin ice, and then in a sort of offline way, computed what change would that have on the heat flux, on the vertical heat flux through the ice. And so these figures just give an example of that offline scheme. The main thing to note here, this leftmost figure is showing the snow thickness on the thinnest ice before we apply our redistribution that is in the current model output. And the thing to note is that the snow thickness on the thinnest ice is very thin. It's much thinner than what we see in observations. However, because the youngest ice doesn't occupy a very large area fraction, we can see on the right here that redistributing snow like this doesn't cause a very large change in snow thickness on the thicker ice. The sort of results from this offline analysis suggested that by not incorporating the snow redistribution, we could be potentially currently overestimating the conductive heat flux in the wintertime by an average of about 6%, although the importance of this increased as we get later in the season when the ice is thicker and more of the ice growth is coming out of the youngest ice. And so I want to stress again that this is an offline analysis, so this doesn't include all of the feedbacks that of course are present in the real system, but we thought that this was enough of an impact, potentially be important to see what impact it might have in the coupled framework. So again, this was an offline analysis, but we did come up with this kind of working hypothesis on what are possible feedbacks we would see if we implemented this into the coupled climate model. And so later on, we'll come back to this working hypothesis with the results of our coupled run and see essentially how close were we. Next up, I'll briefly describe our snow redistribution scheme. Just to refresh everyone, or maybe for some of the land ice folks who are here, within each grid cell in CSM or CEIS, the ice cover is broken up into a finite number of thickness categories, usually 5. And on each thickness category, the ice is assumed to be uniform thickness and to have a uniform thickness of snow on top of it. And the default setup for CEIS is that there's no snow redistribution between thickness categories. So snow only accumulates on each thickness category with precipitation. And what that means is that the youngest ice, which has experienced few or no precipitation events, often has very thin snow in the winter. Now, the ideal snow redistribution scheme might look something like this, where when the wind blows, we would take snow off the thick ice and redeposit it onto the thinnest ice. And for this sensitivity study, we chose not to do this, in part because there are a lot of observationally uncertain parameters related to the erodibility of the existing snow, that snow's microstructure, the impacts of topography. And so instead what we did was we took this idea of a sort of minimum snow thickness from redistribution that we had seen in our observations, and we said, what if we just preferentially direct the incoming snowfall to the thinnest, or to the ice categories that have less than this minimum thickness, to effectively model the effect of as if snow had fallen on the ice and then the wind had redeposited it shortly thereafter onto the ice that had below the minimum snow thickness. And it's, in the Arctic, especially in the winter, it's very windy a lot of the time. So we think this redistribution happens pretty rapidly. And so with this scheme, all we need to set is what is the minimum snow thickness that we think redistribution should deposit onto young ice. And then we simply preferentially shunt precipitation to achieve that. So we've implemented that in a source mod with CEIS, and we've now run a 50-year run in the pre-industrial control climate with these modifications. And in kind of the results I'll show the remainder here, we compare that with the control run that is runs without this modified snow redistribution process. And so I'll begin here by saying at the outset, we don't see an evident mean ice thickness change. So the mean ice thickness between our modified run and runs that didn't have this snow redistribution, we're basically within the range of internal variability. And so, for example, the plot on the left here is showing the mean ice thickness across a large region of the Arctic from September through August. And what I'm showing here is basically the mean of these 50-year runs. So the black line is our modified run, including snow redistribution, and we take the mean across all 50 years. We're comparing this with an identical pre-industrial control run. These are the tuned ice runs that Dave Bailey ran, were used in Jen Kay's paper. And that run was much longer, so I've broken it up into 50-year non-overlapping chunks, and I'm just comparing those with our 50-year simulation. So the spread in these colored lines gives us a sense of the kind of internal variability in the pre-industrial control. And the short takeaway is that in terms of the mean ice thickness, we don't see any difference from internal variability. Interestingly, we do see a difference in the mean snow thickness. So in our snow redistribution run, the snow thickness that accumulates on the ice is about 2.5 centimeters lower. And we'll show later that this is due to actually increased snow ice formation in the modified run. Although we don't see a change or a change outside internal variability in the mean ice thickness, we do actually see significant changes in the ice mass balance terms. So this figure here is showing the difference in the ice mass balance term between our modified run and the control. So for example, the fact that all of these blue bars are negative, that means that we are getting less congelation ice growth in our modified run than is present in the control, basically throughout the winter. And so as predicted, we do see less congelation ice growth due to this decreased heat conduction. However, there were a number of effects that we hadn't predicted. Notably, in the wintertime, we have increased snow ice formation, which perhaps we should have predicted a bit better or hypothesized better. But we have other sort of surprising things like this increase in frazzle production that increases as we get later and later in the winter. I probably won't have time to discuss this in detail, but I think this is due to actually an ice strength feedback mechanism that's occurring. Happy to discuss that more with anyone later. The other sort of surprising change for us was that we actually saw an increase in surface melt in June and July in our modified run. So these bars are more negative, as in there's more surface melt. And the reason for that is because of this reduction in snow due to the snow ice formation, we have a smaller snow fraction in June and July that's leading towards lower albedos and actually more surface melt, so contrary to what we expected. We can aggregate and look at these differences across different regions, but I think in the interest of time, I'll just focus on the sort of the weighted average across all regions here, in which we see that annually, the growth season changes in the mass balance terms more or less balance each other out. So we do see a significant decrease in the congelation ice growth, but that's largely balanced by the increased snow ice formation and the increased frazzle growth, which I think is really interesting. We do see a net change that is slightly negative. So in the pre-industrial control, accounting for this snow redistribution does seem to slightly reduce the amount of ice growth, but it's simply not enough of a change to bring the mean ice thickness outside the range of internal variability.
David, just a couple minutes.
Couple minutes? Okay, I think we'll be okay. So the final thing I want to, I think the final thing I want to share here is that although we don't have a mean change in the ice thickness, we do see changes in the ice thickness distribution. So the mean's not necessarily changing, but the distribution is. I've been exploring a bit on how to actually present this, because a change in distribution is kind of a hard thing to show. But the plots here are basically showing in the X, this is showing the per category change in ice area fraction. So for example, the fact that ice thickness category 1 is to the right here in January means more of the ice area is in thickness category 1. And the y-axis here is showing the change in the ice thickness. So these plots are showing that ice category 1 is both occupies more area in our modified runs, but is also a little bit thinner. And so on net, I think the impacts here are that the snow redistribution on young ice is making it harder for ice to thermodynamically graduate kind of out of this thinnest category. And that's maybe increasing the role of dynamics in producing the ice cover that we see. I think in the interest of time, I'm just going to skip over these last bits. But our hypothesis was partly right, but also partly wrong. We certainly are seeing some different effects than we had expected, especially downstream. And so we now have an updated kind of working hypothesis based on the possible feedbacks that we're seeing, which if anyone is interested in or has questions about, I'd be happy to discuss more offline. And our next steps are to repeat this analysis in the historical and 21st century period. So sorry I'm a little bit over, everyone, and more than happy to take questions in the chat or via email or elsewhere. Thanks.
Thanks, David. So it looks like you do have several questions in the chat. So if you could address those there. And I mixed up the order of the talk. Sorry about that. Lorenzo was supposed to go first and then David, but we'll get back on track now. So I'm going to turn over to Lorenzo Zampieri, who's going to be talking about sea ice model complexity. So take it away.
Yes. Okay, great. Yeah, today I will talk about sea ice model complexity. Yeah, my name is Lorenzo Zampieri. I'm a new postdoc here at Anchor. And actually this work has been done during my PhD at the Alfred Wegener Institute. Okay. So just introductory slide about sea ice modeling. So what I think it's very, sorry, I'm minimizing. Okay, great. Yeah. So what I like to have in a sea ice model, or what I would like to have in a sea ice model, is that this model is understandable, easy enough to implement, should be energy and mass conserving, efficient, compatible with other model components, and also compatible with and comparable with observations. And the way we do this is to define variables that describe our sea ice, so how compact it is, how thick it is. We discretize these variables over a domain. And in this case, I'm showing an unstructured discretization because the model I will use is an unstructured model. Afterwards, we determine basically how sea ice moves in response to external and internal forcings. And yeah, basically by solving the momentum equation, we find our velocity. And afterwards, the second step is to add back our sea ice variables with the ice velocity. So we distribute those variables in the domain. And finally, we determine how sea ice grows and melts and interacts with the radiation. And in the rest of the talk, I will focus in the last process, on the last processes. So when it comes to sea ice model and model complexity, so this is just part of the story because there are a lot of competing interests in the field of sea ice. People want high resolution. At the same time, we want simple implementation to interpret the results. We want computational efficiency. And of course, we also want complex and detailed physics. And an additional complication is that these models need to work well for a range of applications. So for operational predictions, but also for long climate projections. And yeah, so actually the work I'm presenting, it's already published and you can find more details in this James publication. Now, when I talk about physical complexity of a sea ice model in the context of this study, I intend the subgrid complexity or the complexity of the subgrid parameterizations. So on the left-hand side, you can see a simple, very simple model version, which was the standard version in the version 2 model. And we see a single class model with the prognostic description of the temperature, just one layer on top of a layer of ice, so-called zero-layer thermodynamics. And we also have a simple description of the interaction between the sea ice and the radiation with constant albedo values. On the left-hand side, you see basically what you are more familiar with. So this is, I would say, a complex model formulation with discretization in the thickness space in multiple thickness classes. We have a vertical discretization of the ice and so we can also have a prognostic description of temperature and salinity. We have melt bonds, we have complex radiation scheme, and many more processes. Now, the question is this complexity important for our sea ice simulations? And the research questions I will try to answer with my talk. are the following. So does a more complex and physically realistic formulation of a CIS model lead to better CIS simulations? And again, how does the impact of different atmospheric forcings on CIS simulations compared to the impact of model complexity? So basically, what's the impact of boundary conditions compared to the impact of model complexity? And to answer these questions, I will use the following research tools. So as I said, I'm using the FESM2 CIS model equipped with the IcePack CIS single column library. So this is, I think those results are interesting also for the CESM community, because the CIS physics, in the end, it's the same as the one it's used in CIS and CESM. I'm using a Green's function optimization approach for tune the model configurations I'm considering. And this tuning is based on Arctic observations, so it will be an Arctic focused study. And as boundary conditions, I'm using two atmospheric forcings products, the NSEP forcing and the RFI forcing. So this study is in the context of uncoupled CIS modeling. And yeah, I mean, it's not clear how generalizable these results are to fully coupled models. So that you are aware of this and keep this in mind. We will focus on 3 different model configurations with increasing complexity. So from C1 to C3, you can see we go from basically a 0-layer single thermodynamics single class model to typical 5-thickness class model with the Bit-Slipscomb thermodynamics and Delta Eddington scheme, which is basically what's used in the CESM2. And for each one of these configurations, I choose 10 model parameters that we know are important in defining the CI state. And I try to optimize these model parameters. So I try to tune them to get the best possible simulations out of these configurations. And this allows us to compare these model setups in a fair way, I would say. So a few words on the procedure we use for the optimization of the model parameter. So it's a very simple approach. We start basically for each of our 3 configurations, we start with a control run. And then for each one of the 10 parameters, we run a perturbed simulation by slightly increasing or decreasing the value of that parameter. Basically, what we can do is to compute a cost function, which measures the mismatch between these runs and a set of observations. And by linearizing the system with the algebraical approach, it's very simple. We end up having some optimized parameters that we can use to run an optimized model run. And this process can be repeated iteratively, and I will repeat it twice for each configuration I'm considering. And I will also repeat the optimization for each forcing separately. So now we come to the result part, and let's start having a look at what happens with the CIS concentration. So let me guide you through this plot a bit. So here on the x-axis, we have the cost function, which basically it's defined by this formula, and it measures the mismatch between observations and the model run. And the idea is that a cost function value of 1 means that the difference between model observation is of the order of the observational uncertainty. Now, here on the y-axis, I have my different model configurations. So for example, C1 for the NSEP forcing or C1 for the RFI forcing. And the circles represent the cost function value before optimization, after 1 iteration, and the small one is after 2 iterations. So you see that the cost function is reduced during the optimization, and this means that the tuning works. So, but let's consider more the results. So we can see that when it comes to CIS concentration, Model complexity seems to matter. So we see that the simplest model has a lower cost function value. And this is true for NSEP. The situation is a bit more unclear for the RFI forcing, but you will see that this model configuration C2E always suffers a bit. So yeah, it's not a great simulation, even though it has been optimized. What we can see is that also there is a boundary condition dependence. So the NSEP forcing definitely performs better than RF5 in terms of CIS concentration. And we also see that the optimization is actually important here, because without optimizing my model setup, I would have drawn the wrong conclusion. I would have just said that the simplest model version is definitely worse, but we see that it can be actually optimized. And also we see that the simplest model version is the model configuration that we can optimize more efficiently with our optimization. Now, interestingly, if we look at the performances in terms of CIS edge position with the integrated ice edge error, we see that by looking at what happens in the Antarctic with the configuration tuned for the Arctic, the model ranking changes completely. And this tells us that our system is probably not able to capture a good CIS simultaneously in the Arctic and in the Antarctic. When it comes to the CIS thickness, the situation is quite different. So we see that the ranking based on the model complexity is somehow broken. And also there is not really a strong dependency on the forcing. We see that in general, we can say maybe that the simplest model configuration is probably the best one, and also the one that can be optimized more easily, given the observation, which in fairness have a quite high observational uncertainty when it comes to CIS thickness. When it comes to snow thickness, the situation is again different. In this case, the model complexity seems to matter. And in particular, there is a process that was not captured by the simpler model version. And this is the fact that when we reach the ice in a multiple thickness class model, we lose some snow in the open ocean. And this process helps to deplete a bit of snow and to get better agreement with the observations. So yeah, in the interest of time, I will try to go quick. When it comes to CIS drift, the situation is a bit more unclear. So please notice that the cost function value are different from before. So we cannot really find a link between complexity and better CIS drift, but this also makes sense because because all the models that we are considering here, the model configurations use the same dynamical scheme. We see that perhaps the RF5 forcing performs a little bit better than NSEP. We can see here just a test case for April 2015, where we have the observations, each configuration for RF5 and for NSEP. We see that RF5 has a bit too much recirculation in the buffer gyre of the ice, but at the same time, it captures a bit better the higher speed that we see in the observations, and this might be due to the fact that RF5 has forcing as a high resolution compared to NSEP. So some final considerations on the role of model complexity. So we said that increased CIS model complexity improves the simulated CIS concentration and snow thickness. And while it's a bit less relevant for the CIS thickness and for the drift, we said also that the impact of different boundary conditions is at least, or can be at least as large as the impact of model complexity. And I showed that simple model configuration seems to be seems to be more easily calibrated compared to a more complex system. So just a couple of words, recommendation for future CIS model development efforts. For sure, it's optimization. So we need to compare optimized model versions in order to draw the right conclusions. And also modularity. I think it's important to keep our models modular. And thank you. I'm happy to take questions. And I just want to advertise this session at the collective AMS meeting in Madison, even though it doesn't really fit with this presentation. But yeah, I'm happy to take any questions in the chat.
Great, thanks, Lorenzo. It looks like there are a couple questions in the chat. So I think in the interest of time, we'll keep moving on, but if you could address them there, that'd be great. So next up, we have Mark England, and he's going to talk about spurious climate impacts in sea ice loss simulations. So it looks like we can see your screen.
Okay, beautiful.
Great.
Is that good?
Looks good, thanks.
Yeah, so I'll talk to you today about work we're currently doing on the spurious climate impacts in sea ice loss simulations. And this is work which was done when I was at Scripps with Ian Eisenman and Theo Wagner. And this is currently in revision at Journal of Climate. And here, the idea is that there's been a lot of interest and studies on the role, especially of Arctic sea ice loss on the climate system. And these are using fully coupled comprehensive climate models, and they show substantial climate responses to this imposed sea ice loss. And so on the left here, this figure comes from Strina 2018, showing a variety of different models, and they've used a variety of different methods to get these results, by showing a really substantial Arctic warming attributable to Arctic sea ice loss, as well as some tropical upper tropospheric warming, this mini global warming signal. And I've also done work on this in the past using these model experiments to investigate the tropical response, showing there's a really pronounced tropical response to both Arctic and Antarctic sea ice loss. And generally, I think that we can categorize the way that people have perturbed sea ice cover in these comprehensive climate model simulations into 3 different categories. The first we named albedo modification, and that's reducing the albedo of the sea ice through changing some parameters of the sea ice properties in the model. This has problems because you can't get enough winter sea ice loss, because you're relying here on the incoming solar radiation, which obviously isn't very much in polar night. The second is ghost flux, and this is where an additional flux is added to the sea ice module, unseen by the other components. And the last is some form of nudging. And there's a few different ways that this is generally done, but the one which is recommended in the polar amplification model intercomparison project, in that paper, they suggest basically removing the sea ice, kind of just removing it at some time scale until you get either the volume or the thickness that you want. And I've shown some studies on the right here, which is a non-exhaustive list of those that have used them. And in this paper, we argue that there is actually a common limitation to all of these methodologies. And that is that they add heat into the climate system, this artificial heating, and that's quite obvious in the ghost flux method, where you're using this flux to melt the sea ice. But we also argue it occurs in the albedo modification method through an anomalous absorbed shortwave flux, or in the nudging method through anomalous latent heating. And the second point is we argue that this spatially varied heating is actually going to generate a climate response of its own, independent from the response to sea ice loss. And so it's going to end up really overestimating what sea ice loss is doing in the climate system. So we first looked at some of the comprehensive experiments to see what kind of order of magnitude heating we think is going on here. On the left, this is the sea ice area. So this is from 2 simulations from Deseret 2015. The black is a control, which we can imagine as some kind of near historical sea ice concentration for the Arctic. This is sea ice area. The gray shading is the sea ice loss they're trying to impose. The green line here is the ghost flux. So you can see it does a good job of replicating. This is end of the century Arctic sea ice conditions under the RCP 8.5 forcing. And the red is through the albedo. So you can see here that if you use albedo modification, they're able to get the right amount of sea ice loss in the summer, but not in the winter. And then in the ghost flux simulations, we're able to estimate how much heating is being added into the climate system. And it's somewhere between 10 and 20 watts per meter squared in the high latitudes, which is being used in order to melt the sea ice, in order to see the response to this sea ice loss. And then we weren't able to do this for the albedo or the nudging because the actual output is really not available for fields we would need to estimate this. But we can ask, so all these studies, they estimate a surface temperature response to Arctic sea ice loss alone. And so the question here is, well, is this a good estimate given that we know that we're heating the climate system by this artificial amount here? And so to do that, we step back, and instead of using these comprehensive GCMs, we turn to an idealized model of sea ice and climate. And this is a modified energy balance model, which was detailed in Wagner and Eisenman 2015. So this is an EBM with an ocean mixed layer, and then sea ice is going to form when the surface is sufficiently cold, and it's going to have seasonal and latitudinal variations. And the sea ice is going to melt and grow based on the physics from the Eisenman 2012 single column model. And in this model, the important thing to take away from it is that sea ice is going to affect climate through two ways. The first is insulation. So it's blanket-like effects, keeping the atmosphere enormously cold in winter. And that is going to depend on the sea ice thickness. And then surface albedo, which in this model just depends on whether there's sea ice present or not. And then if we look at the governing equations for this model, it simulates the evolution of the enthalpy E, as shown here. And we're thinking about the surface and the overlying atmospheric column. And this enthalpy is going to be governed by a balance of the absorbed solar radiation, which is shown here, a linear representation of outgoing long wave radiation, a diffusive approximation here for atmospheric transport. F is some sort of constant, which we're going to use as a climate forcing, analogous to increasing CO2, and FB is flux coming from the deep ocean. But what's important really in this model, and what's powerful about it, is if we take the annual mean here, and the annual mean is denoted by the overbar, we get the following equation. And we can think about sea ice loss as a perturbation from a control. So we're going to call that this delta. And I won't go through the derivation, but the result is we can think of the Northern Hemisphere average response to sea ice loss in this model. It's easily calculated in this idealized model as this. And that is just saying it is some, it responds to the forcing, delta F, and then also is dependent on some change in the albedo. So importantly here, it is not dependent on changes in sea ice thickness or the enthalpy, and that will be the insulation. And similarly, we can look at the deviation from a Northern Hemisphere average that is shown here. Here we can't actually solve it quite so nicely, but we get this implicit equation here. And as you can see, the change in the latitudinal variation of the surface temperature, as shown in this on the left-hand side, is just going to depend on the change in the albedo. Again, so crucially, the only impact of sea ice changes on the surface temperature response in this model in the annual mean is through the surface albedo. And this is saying that the insulation is important for seasonal effects, but not on the annual mean response. And so this is really a powerful thing in this model, because the insulating effects of sea ice albedo basically cancel out in the annual mean, and the surface albedo is a thing which is going to be the only driving factor for how sea ice is going to affect the surface temperature. And why is this powerful? Well, this is good because we've disentangled these two, and then we can, by specifying the surface albedo, we can isolate the true role of sea ice loss in this model. And then we can use this as a benchmark, and we can see how other methods are performing against this benchmark. And so to find this true role of sea ice loss in this model, we have a control simulation here with a climate forcing of 0. We have a future where this gets about the same sea ice loss as end of a century conditions. And then we have another experiment where we specify the surface albedo from the future, but we have a climate forcing of 0. And so the difference between the control and the future will give you the total warming, and the difference between the control and the specified albedo experiment will just give you the role of sea ice loss alone. And this, again, is a really powerful use of the idealized model. And then we end up replicating the other 3 methods in this energy balance model here. And you can see that the black line is some sort of historical sea ice. The gray shading is the sea ice loss we're trying to replicate approximately by the end of the century. And then the green and blue lines do a good job of this. This is the ghost flux and the nudging. We have an experiment which is the red dashed line, where we try and replicate the summer sea ice loss using the albedo modification method. And we have the solid red line, which gets the right amount of annual mean sea ice loss. And we can estimate from these how much heating they're adding into the system. So on the left is the result I showed you before from a comprehensive model. And on the right is the same for the idealized model. So there are lots of similarities and there's some differences between the two, but we can see that all of these methods are adding in artificial heating into the Arctic, somewhere between 5 and 20 watts per meter squared at different latitudes. And I'll spend some time now talking about the main result. Everyone was kind of leading up to this and trying to kind of walk you through our thought process, but this is the takeaway message here. So this black line is just the total warming after about a 3 watts per meter squared increase of radiative forcing in this model. And you can see it's polar amplified. And then we can isolate the true role of sea ice loss alone in this model, which is the gray line here. So you can see that all of the Arctic amplified response is coming from the sea ice loss, which we would expect because this is the only nonlinear feedback in this model. And what's nice is that the difference between the black and the gray line is this uniform warming, which is exactly what one would estimate from the direct radiative forcing without any nonlinear feedbacks. And then if these all these different approaches were doing a good job, they would hit the gray line. That's what they're trying to replicate. But what we find here is that all of these different methodologies actually substantially overestimate the role of sea ice loss in this idealized model. And they actually, all the solid lines, which are the ones with the right annual mean sea ice loss, end up substantially overestimating by a factor of 1.5 to 2, and actually end up hitting the black line. They're much closer in the Arctic to the black line, and that suggests they're conflating the radiative, the response to radiative forcing, and the role of sea ice loss, and they end up substantially overestimating it. And even the red dashed line, which is the albedo modification one, where we're just hitting the summer sea ice loss, that still overestimates it. And here, I'm not trying to say that we know exactly how much they overestimate it in the comprehensive models, just that this is a kind of a back of the envelope approximation in this idealized model, which can help us inform our understanding of what's going on in the GCMs. And so the conclusion here is that we've used this idealized model of sea ice and climate, and it's a really great tool because it allows us to simplify a lot of things. And in the annual mean, but sea ice is only going to affect the climate through changes in surface albedo. And that allows us to isolate what sea ice is really doing in this idealized model. And we find that all of the standard methodologies which have been extensively used, they overestimate the annual mean surface warming attributable to sea ice loss in this model. And they do this because they conflate that response with that of radiative forcing. And so really the takeaway here, I think, is that the climate impacts possibly associated with sea ice loss in GCM simulations has likely been overestimated. And that's somewhat interesting because there's a current debate about whether these simulations are actually underestimating the response to sea ice loss. So there are a lot of caveats here about what this model does and doesn't include, and I'd be happy to kind of answer any questions about that. But I think the message I want to get across is that if these methods don't work as aimed in these very idealized models where we understand what's going on, I don't think we should be confident we have a good understanding of what's going on in the comprehensive GCMs. So with that, we'll end. Thank you very much.
Thanks, Mark. It's a great talk. So I think we're going to keep moving on in the interest of time. There are several questions in the chat for you. So if you could address those there, that would be great. And people feel free to continue putting questions in the chat as they occur to you. So, so next up, we have Andrew Pauling. And Andrew's going to talk about feedbacks, climate sensitivity, and polar amplification insights from volcanic eruptions in large ensembles. So.
Great. Does that look okay?
It looks great. Yep.
Cool. Thank you. Yeah. So today I'm going to talk about some ongoing work I've been doing, seeing what we can learn about polar amplification and more generally feedbacks and climate sensitivity from volcanic eruptions, making use of the recently available model large ensembles that have kind of come about in the last few years. So some background on this. So this work started by looking at the sea ice response to volcanic eruptions in both hemispheres. So we got interested in this a couple of years ago. And there are some large volcanic eruptions in the historical period that provide some useful case studies. So from about the 60s onwards, there were 3 really large volcanic eruptions. And we chose to focus on using the eruption of Mount Pinatubo in 1991, since that's the biggest of those eruptions. And the forcing that it produced was roughly symmetric between the 2 hemispheres. So it provides a fairly uniform forcing globally. And so for those not familiar, this is the radiative forcing from the Mount Pinatubo eruption. So that's the big negative spike here in black in this plot. So in 1990, the volcano went off in 1991, and the total radiative forcing lasted for a few years afterwards. So that was mostly from the shortwave forcing. So the eruption introduced sulfate aerosols that reflect incoming shortwave radiation. And there's a smaller positive longwave forcing as well. So this is data from Schmidt et al. 2018, who produced an estimate of the radiative forcing from that eruption. The smaller eruption in the 1980s is the Chichon eruption, which was smaller and mostly confined to the northern hemisphere. So we didn't focus on that one so much. Spatially, the forcing looks like this for the Pinatubo eruption. So on the top, we have the short wave, then the long wave, and then the total forcing. And so you can see it's the eruption occurred in the tropics, and then the sulfate aerosols get dispersed poleward in both hemispheres over time. And so you end up with a roughly symmetric forcing between the 2 hemispheres. And again, this is from that reconstruction from Schmidt et al. 2018. And so last year we published this work in GRL, looking at the sea ice response. And so here I'm showing the sea ice area and sea ice area anomalies following the Pinatubo eruption. So on the top left here is the Arctic sea ice response. On the left-hand side is the Arctic sea ice response in CMIP 5 generation models on the top and CMIP 6 generation on the bottom. And then on the right-hand column, I'm showing the Antarctic sea ice response from the same Pinatubo eruption. And so clearly in the Pinatubo, in the Arctic, you get a small increase in sea ice area for a couple of years following the eruption, and then the decline from greenhouse gas forcing kind of resumes. That response is less clear in the Antarctic. The Antarctic response is a lot messier, and yeah, it's hard to see a consistent signal between models in the Antarctic. Something that then grabbed our attention in this work was looking at the temperature response. So here I'm showing the zonal mean temperature response to the Pinatubo eruption in those models. And so here the blue line and the black line are the multi-model mean zonal mean temperature response to the Pinatubo eruption. And then the green line here, I've scaled and flipped the sign of the fast response to 4 times CO2 greenhouse gas response. So that's the temperature response you get in the first 10 years of that simulation. And we picked that because this kind of spatial pattern reminded us of that fast response where you get polar amplified warming or cooling in this case in the Arctic, and a kind of subdued response in the Antarctic. And so we were interested in the differences between these two forcing scenarios. And the thing that grabbed our attention here is that the Arctic response in particular is less polar amplified in response to a volcanic eruption than it is to an increase in CO2. So there's more cooling in the mid-latitudes, or there's a less of a difference between the mid-latitudes and the poles in response to the volcanic eruption than there is to CO2 forcing. And so we're interested in kind of understanding why that is. And so that's been the focus of my work since this work came out last year. And so the first thing we kind of thought of to tackle this was looking at the vertical structure of the temperature change, which is quite different between the two cases. So here I'm showing the response in CMIP6 models. On the left is the response to the Pinatubo eruption, so latitude versus height here. And so there's a reasonably uniform vertical cooling. Reasonably uniform cooling in the vertical in the Arctic in response to that volcanic eruption, versus the response to the CO2 forcing is much more surface trapped with the familiar kind of polar amplified surface warming. And so that would lead us to expect a different lapse rate feedback in the Arctic, since the vertical structure of the temperature change is so different. And so to get at this with a really big signal so that I could be sure what I was seeing was real, instead of using the Pinatubo eruption, which is a reasonably small signal to noise ratio, which is why we've needed to use these large ensembles, I looked at this in the CESM last millennium ensemble, which has some really gigantic volcanic eruptions that kind of give you a really big signal to noise ratio so that I could look at the mechanisms more easily. And so here I picked this largest eruption in about 1257. And so this is the zonal mean temperature response to that eruption shown on the right. And so it is polar amplified in the Arctic, but less so than the 4 times CO2 case would be, warming would be. And so this is the kind of time evolving temperature response to that eruption on the top here. And so it's a reasonably similar spatial pattern to the Pinatubo eruption, reasonably symmetric between the two hemispheres, a little more cooling in the Arctic than the Antarctic. And so it provides a reasonable analog to the Pinatubo eruption, just with a much bigger signal. And so first I then use the output from these model runs to compute feedbacks and compare it to the 4 times CO2 case. And so first I computed the surface albedo feedback. And so the blue lines here are showing the response to abrupt 4 times CO2, and the orange lines are showing the response to the volcanic eruption. And so in the Arctic, you have a much weaker surface albedo feedback to the volcanic eruption than you do to the 4 times CO2. So the solid lines here are normalizing by the global surface temperature change, and the dashed lines are normalizing by the local surface temperature change. But in both cases, you get a weaker surface albedo feedback. Similarly, so the one we were really interested in looking at is the lapse rate feedback on the right here. And so in the Arctic, again, the orange lines is showing the volcanic response, and the blue line is the 4 times CO2 response. And there's a much weaker, or noticeably weaker lapse rate feedback in the Arctic in response to the volcanic eruption. The reasons why this is, well, this is what we expected for the lapse rate feedback, given that vertical structure of warming. There's a weaker lapse rate feedback in the Arctic. Why the surface albedo feedback is so different, we're still working on. But so there is at least a mechanism here for why that Arctic response is less polar amplified in response to the volcanic eruptions. Something else I've been interested in using these volcanic eruptions to work on is climate sensitivity. And so there's some work in the past claiming that climate sensitivity can be constrained by looking at the response to volcanic eruptions. So there was a study by Bender et al. In 2010 that used CMIP3 model simulations to come up with a constraint on climate sensitivity. But they had very few models and very few ensemble members with which to make this constraint. And so I was interested in trying to build on this work with the much bigger output available from CMIP6. And so these are the models I've been able to use so far from CMIP6. I picked the ones that had at least 10 ensemble members in their historical simulations. And so I have, I think, 12 or 13 models so far that have at least that many ensemble members. So we have a lot more simulations now than back in CMIP3. I think the paper that Bender published only had 13 ensemble members total between all of the models they had. So we've got a much bigger set of data to work with now. So as a reminder, here I'm using the Pinatubo eruption to try and build this constraint on climate sensitivity. And so it has that negative forcing in 1991. And so this is the temperature response to that forcing. So I've detrended the temperature anomaly in each of these models. And so this is dip following the Pinatubo eruption, and then a recovery over about 5 years following the eruption. And so each of the colored lines here is one of the models that I used, with the shading showing the standard deviation around that. And then the black line here is the ERA5 reanalysis. So the models are reproducing what happened in reanalysis pretty well. Similarly, this is the TOA shortwave anomaly in all of those same models with the ERA5 reanalysis overlaid as well. It's notable that many of the models have a stronger TOA shortwave anomaly than what's shown in reanalysis. But they are doing roughly the right thing. So that, as I mentioned, this Bender et al. 2010 study used CMIP3 model, the CMIP3 model response to Pinatubo to constrain climate sensitivity. They had 10 climate models to work with 12 total ensemble members. And they claimed that you could create a linear relationship between volcanic climate sensitivity, which I'll define in a second, and effective climate sensitivity, as usually defined from 4 times CO2 or 2 times CO2 simulations. And so the volcanic sensitivity, they defined as the ratio between the temperature response and the shortwave anomaly integrated over 5 years following the eruption. So you integrate the total, you integrate the temperature response over the 5 years, and then integrate the shortwave anomaly over the 5 years following the eruption, and then take the ratio of the two. So that gives you an idea of how sensitive the climate is to the anomaly caused by the volcanic eruption. So first, they just looked at the temperature response alone. And so on the left here is their figure from that paper and using CMIP3 output. And there's not a very strong relationship here between the integrated temperature response on the y-axis and climate sensitivity of each model on the x-axis. And so I reproduced this for the CMIP6 models that we have, which, given that they have so many ensemble members, I can also get an uncertainty range. And so again, I also find no strong relationship here. So far we're consistent. Then they looked at the integrated TOA shortwave anomaly, integrated over the 5 years after the eruption as well. 3 years after the eruption for the shortwave anomaly. And again, there's something of a relationship here if you ignore this INM CM3 model, which they did in their paper for a lot of their analysis, because it seemed to be an outlier for a lot of things. So there is some relationship here. And then I reproduced this with CMIP6. And if you only included the models up to here, I also get a similar response. These two, I'm not sure what's going on, but they're kind of break the relationship a bit. So not really sure whether we agree here or not. And then finally, I used the metric that they did, that they claimed can constrain climate sensitivity which is the ratio of those two things I just showed. So the ratio of the temperature response to the shortwave response. And they claimed this linear relationship, which they could use to constrain climate sensitivity. When I do the same thing, I don't get such a strong relationship. So it seems with the addition of a lot more model output, this relationship doesn't hold up so well. Something I was interested in thinking about was maybe the cloud response is messing things up because they're using the net shortwave anomaly instead of the actual radiative forcing. That can be kind of muddied by the cloud feedbacks. And so I use the APRP method to separate the contribution from clouds and non-clouds to the shortwave anomaly. And so here, I'm only using the component of the shortwave anomaly that's due to non-cloud effects. And so while there's not a linear relationship between climate sensitivity and this ratio, there is some sort of distinction between the high sensitivity models and the lower sensitivity models that I'm kind of interested in pursuing. And so that's ongoing work that I'm working on right now. So in summary, there's a less polar amplified response to volcanic eruptions than to greenhouse gases in CMIP6 models. The vertical structure of the temperature response explains some of this through the lapse rate feedback in the Arctic. There's also a weaker surface albedo feedback that I'm interested in trying to understand better. And also these volcanic eruption simulations are not such a good climate sensitivity as maybe past work has suggested, at least from what I've been able to find so far. Thanks.
Great, thanks a lot for a very interesting talk and an interesting set of talks. So if you have questions for Andrew, please put them in the chat. And it looks like we have a pretty active chat going on. So we now have a break that's scheduled until 2:45. So we didn't want people to get too much Zoom fatigue. So please take a break till 2:45, come back promptly then, and we'll start off with Ed's talk. And you don't have to leave the meeting. You can just, mute yourself and turn off your video and continue to check on the chat and answer questions and have active discussion there. So thanks again, and I will see you all in about 20 minutes. Hey, Dave.
Hi there.
If anybody is sitting and wants to chat, feel free to turn on your camera and your microphone and we can have some casual conversation over coffee.
Hello.
Hey, I miss the coffee breaks. It's like, you know, these Zoom meetings. So.
My sister-in-law, when she has she leads some seminars sometimes, and when it's with her group, when it's internal group or something like this, she makes sure that everybody receives like a package at home, so that everybody can open it, and so they share this moment together.
What a great idea! Yeah.
I'm not sure we have a budget for this, but
Yeah, I did say run that one by Gokhan.
I don't know how much money we. Well, Elizabeth says I've seen those companies, so.
Hey, David. Yeah. How are things?
So it's raining here.
It's raining.
Yeah, which is a little down, a little bit of a downer. It hit 60 degrees yesterday, which has been interesting. But
Probably not normal March weather for you.
not really. We tried to go kayaking, but the river was still pretty solidly ice dammed. So
Yeah.
But where you at, David?
I'm in New Hampshire.
Okay.
Yeah, it's cold here right now, but last week it hit 70 or something. So, and it was raining Friday night. Crazy. It should not rain in March.
Yeah, we had like a crazy, like 70-degree Fahrenheit swing.
Yeah.
Yeah, it's.
Hey, Dave, are you in California? Are you in Boulder or?
Okay, yeah, maybe you can see the surfboard. I'm in California.
Yeah, you don't really need a surfboard in Colorado.
Yeah, I'm a little bit jealous of the winter storm that came in, it sounds like.
Why are you jealous?
Oh, I love the snow. I love winter.
Yeah.
Not much of a warm climate person.
This one wasn't that impressive. Maybe a couple inches. I don't know about Boulder, but at least at my house.
We probably got, I don't know, I'd say 4 or 5 inches here. But I think, like I read Steamboat got hammered. So
Right.
if you were in the right place,
Right.
right set of skis, you probably were enjoying things.
Uh-huh.
The Western Slope needs it. That's good.
Mm-hmm.
Yeah.
How are you guys all doing?
Pretty good. Looking forward to in-person meetings. But I don't know.
Yeah, I feel that after I did ocean sciences last week, and that was my last virtual meeting, I think.
Yeah, it's just tough. I mean, like, I like all of you. It'd be nice to go get a beer after the meeting's done or chat over coffee, or I don't know. It's not as satisfying. I mean, it's great to see people's science, and I'm glad that we can still, see other people's science. But yeah, the annual workshop, they're thinking they're going to try and have it in person. I mean, I think it's still kind of a little bit questionable, but they're looking into having it in person. And the tutorial, I don't know if people got an email, the CESM tutorial, the plan is to have it in person. So if anybody's interested in going to that.
Yeah, it's a try.
Right, again, everything's uncertain, right? But at least it seems like it's shifting. Although Hawaii last week I would have been fine. So
yeah. Is the workshop in June? Is that right?
yeah.
Cool.
Yeah. So we'll see. I mean, It'd be nice if it was in person though. Anyway, yeah, Elizabeth just put in the chat, so it's June 13th to 16th. So, yeah. So it looks like it's past 2:45. So bad at being on time. So we're going to go ahead and get started for the second part of the day's science talks. And yeah, and as Christine Shields just put in the chat, the tutorial application's open today. So I did want to make sure people were aware of that, either for yourself or for graduate students or postdocs. And the hope is that it will be in person in August. So definitely, if you're interested, we encourage you to apply. So we're gonna move on to another set of talks. Oh yeah, Dave just mentioned that the tutorial is the same week as the AMS Polar meeting. So that might be a challenge for some of us. Anyway, so we're gonna move on to Ed Blanchard-Rigglesworth talk on the impact of winds on Arctic climate. And so Ed, hopefully you can share your screen.
Yeah, can you see that?
Looks good.
Great. Yeah, and well, first of all, I want to say thanks to everyone that organized this meeting. It's always really fun, and it's great to see familiar faces despite being virtual. So I want to talk about, this is my rather pithy title. I'll describe a little bit more in the next slide, but first I want to thank Lady Roach, who was a postdoc here at the UW, and she did a lot of the analysis I'm going to show. But I also want to thank Qinghua Ding, who I've been collaborating with and done a lot of other work with kind of these type of simulations over the last few years. And as always, thank the Polar Climate Working Group for your, a lot of computing assistance and computing time and assistant with the nudging module. That was Pat Callahan. So yeah, very crucial parts of this work. So what I want to, the motivation questions for this work is basically how much can winds explain temperature and sea ice variability and trends in the Arctic? And basically the kind of the big picture question is if a model happens to have the right atmospheric circulation, how well does it simulate other climate components? We know there's a huge amount of internal variability in the Arctic, and even with really large simulation ensembles, you're never randomly gonna capture exactly the right observed atmosphere. And then a slightly another aspect we think about a little bit is how important are the initial conditions, kind of in the beginning of the satellite era, to understand the climate trends over the last 40 plus years during that satellite era that we've observed in the Arctic. And to answer these questions, we're going to take a CSM1 lens, which is the well-known model that I don't need to explain to this audience. And what we do is we run the same historical forcing simulation from 1979 to 2018. And the only thing that is different is that we nudge the wind in the model. We actually nudge the sort of anomalous winds from the reanalysis. So we take, we calculate what the anomalous wind is in the reanalysis and we apply that to the model climatology in the winds over 79 to 2018. And we only do that over the high latitudes, poleward of 60 degrees. And we actually only nudge the wind from the top of the atmosphere to the top of the boundary layer. So the winds at the surface are kind of free running. And because we were wondering if by nudging all the way to the surface, whether that would sort of mess up a little bit, that kind of surface coupling. We have checked a little bit, doing that to the surface. It doesn't seem to make much difference, but anyhow, this kind of the general setup. And the first thing I want to show is what the surface pressure trends look like. All the trends I'm going to show are from 79 to 2018, so the 40-year period. And I normally like top row summer, bottom row winter, and observations or the era-interim reanalysis on the left, lens mean in the middle, and then the nudged means on the right. And something I forgot to mention, we run a few different simulations of the nudge run where we just sample different climatologic, different initial conditions in 79, like high climatological and low sea ice conditions, but everything else is the same. So it's like a mini ensemble of nudge simulations. But anyhow, so when you look at the surface pressure trends, two main things I want to highlight. In the summer, there's been a higher pressure trends over Greenland and just north of the Greenland and the Canadian Arctic archipelago. So a strengthening of the high there, and then there's been a low over the Laptev, and this has produced actually a sort of enhanced ice export over the Fram Strait, like out of the Arctic and into the Atlantic. And if you look at the lens mean, there isn't really much of a sea level pressure response and you can think of this as the model's simulated force response, right? Because it's the ensemble mean. So this kind of the anthropogenic or the response to climate forcing. And on the right, you can see the nudge simulation, which this is also a good safety check, right? This should look like the observations, right? Because that's the goal. And you can see that it does a pretty good job of simulating the observed pressure trends. And then in the bottom, you see in winter, we mainly have a really big strengthening of this, I guess the Siberian high is a little to the east of the center here, but basically increased heights over Siberia and lows over Canada. So quite a different pattern to the summer. And again, this is not part of the force response in lens mean. So when we look at the surface temperature, looking at the summer, there's kind of fairly uniform warming. It does tend to be stronger over land, over Europe and East Asian observations. Fairly low warming actually over the actual Arctic Ocean, despite the loss in sea ice. And that's probably, because the surface temperature is tied to the melting point during the summer. And you see that the model actually simulates a bit more warming right over the Arctic Ocean. But in terms of the geographic pattern, the force response doesn't really get you much of the observations, whereas the nudge simulation does, slightly enhanced warming over Europe and Eastern Asia and reduce warming over the North Atlantic or even a bit of cooling. A bit more interesting in the winter, you see very strong warming over, centered over the Barents region and observations. This is again captured in the nudge simulation, whereas the forced response in the lens mean has the enhanced warming over the Pacific sector of the Arctic, so more the Chukchi and East Siberian. Another interesting fact is that we've actually seen cooling over Siberia over the last 40 years in observations, which is not part of the force response, but is seen in the nudge simulation. And this is related to that enhanced high pressure and Siberian high I showed you in the previous slide. So far, these nudge runs do a pretty good job at capturing temperature variability at the surface, and the same it's at the middle troposphere, but I won't show that. When you look at the time series of the trends, this is the now temperature average over the Arctic cap north of 70. So on the left, this is just the annual time series. And in black, I show a couple different estimates from observations. In the red is the nudge simulations have three numbers. You can see that they're all fairly similar to each other, right? So by having the prescribed circulation, that really constrains the patterns of internal variability, and they do a pretty good job at capturing the observations, right? So the match between the red and the black shows you that the nudge simulations are doing pretty well. But it's quite interesting when you look at the monthly trends in air temperature. So we've seen that the observations have warmed more than the lens in the winter and spring on the left side of this panel. So these are the temperature trends over this domain for each month. So you see enhanced warming in winter and spring, and even in April, it's outside actually the range of lens. The individual members in lens are shown in the light blue, and the model mean, the ensemble mean in the bolder blue. So we see that enhanced warming in winter and spring, but actually less warming in summer and fall, which is interesting. And you see that the nudge simulations, they kind of try and get that observed enhanced warming in winter and spring, right? They're doing better than the lens mean, but they don't quite get all the way there. And in the summer and fall, they also don't quite correct this bias when you look at the area averaged temperature trends. Now moving on to sea ice. when we look at the interannual variability on the left, I'm showing here September sea ice, and I'm actually showing now 3 estimates from observations in black. And you can see that the nudge runs do a pretty good job. The correlation is 0.92 before detrending and 0.64 after detrending, right? So basically, if CSM1 has the right winds, it's doing a pretty good job at simulating September sea ice, both in terms of the trends and the internal variability. But when you look at the monthly trends on the right panel, somewhat related to the previous figure, we see that there's a really big difference across different seasons, right? So if you look at September and October, these are actually the months that the model's doing the best. So in red, I'm showing you again the nudge run, so it's matching the observations really well. But the rest of the year, there's this bias, and observations are losing sea ice way faster than the model, right? And for, you know, from November to July, it's actually outside the range. Like none of the single members in LENS gets close observations, and given LENS the right winds, it's not improving this, right? So this is really interesting that despite having a better, you know, despite getting those temperature and surface winds pretty well, the sea ice in winter and spring is not showing a corresponding improvement. So that was a surprise to us. Now, we looked a little bit into this, and when we did a regional analysis, so what is the source of this winter bias in the sea ice trends? And it's quite clear. What I show you here are the March sea ice extent time series in the Atlantic in the top panel, and in the Pacific in the bottom panel. And you can see immediately that the main bias is in the Atlantic, right? So you see in observations, we've had a pretty strong decrease in sea ice extent in March, and in LENS, there's a very small trend, right? And it's the same in the nudge runs. Despite getting the internal variability, right, you can see that the ups and downs in the nudge runs match observations pretty well, but the trend is just totally off. With the Pacific, there's better agreement. There's less of a trend in observations in the Pacific. So looking at this, the patterns of sea ice concentration trends now in March, this in complementing the previous slide, you can see, you know, these really big differences, right? Like in the observations, we've lost a lot of sea ice in the Barents and in East Greenland Sea. And actually, the Barents is the region of strongest warming globally, like in those winter surface temperature trends, which, as you might remember, the nudge simulations was doing pretty well, right? The nudge simulations were in a lot of strong warming here, but if you look at the sea ice response, it's much weaker. So that's I think pretty interesting, and it's not just that it's getting the right surface temperature trends, the nudge simulations, but here I show you the trends in meridional winds in the winter in DJF, observations left, model mean, LENS model mean middle, and the nudge on the right. So positive values here are enhanced southerly winds in DJF, right? So this is just to really convince us that the nudging is doing the right thing with the winds, right? So if you compare the right panel with the left panel, you're getting the right trends in southerly winds over this region, which is tied to that large-scale circulation pattern I showed earlier. But the sea ice is just really not responding very much at all. Moving back to understanding the trends in September in the sea ice loss, and I'm getting to the end. I think I've got a minute left, or two, but my timer just died. So anyway, we're interested in seeing why is it that enhanced loss in sea ice in September in the nudge runs compared to the model, and does a really good job of getting the observations. And basically, we think it's a big part of it's the summer circulation pattern of the low over the Laptev, or kind of northern Siberia here, and the high over the West Arctic. So you have enhanced southerly winds over East Arctic and northerly winds out of the Fram, shown by the vector fields here. And that has produced, we looked at the southward ice velocity across the Fram, which is higher in the nudge than in LENS mean. And actually this variable, which I haven't seen in previous studies, it helps explain actually also the intermodal trends in LENS, which is shown in the right panel. So basically, one of the main mechanisms we believe is happening for the September trends is just this kind of summer pattern in circulation and the surface winds. And finally, this is my last slide. One of the questions is, well, is this pattern that gives you that extra sea ice loss in September and matches observations really well? Is that internal variability, or is it a forced response that the model doesn't, like a bias, like a bias in the model? And we can't answer that question, but we thought it'd be interesting to look at the pattern that helps explain model trend variability in CSM, which is shown on the left. So this is the regression of Z500 heights on September sea ice trends across lengths. So basically in the model, when you have higher heights north of Alaska, you have enhanced sea ice loss in September. And if you look at the difference between the nudge and the lens, which is the same as between the observation and the lens, basically this pattern isn't quite the same as this one on the left, even though the sort of local footprint at the surface, right? Because you imagine this pattern on the left, this would give you enhanced southerlies in the lap turf. Probably not really much in terms of, this is at Z500, but I do think you get a bit more northerlies in the Fram. But so the kind of similarities, but also it's not very clear that, this pattern is fairly different to this one. So that's still an open question. And I will leave the summary there. I do want to point out Tsinghua has a parallel study. They focus more on the summer, but the results are consistent with ours. So basically, that the observed winds have given you an enhanced like 20 to 25% of sea ice loss in September. Still a big question whether that is truly internal variability or just a forced response that the model has not simulated. And I think the other main result is this result in the winter and spring, right? That why do these biases in the sea ice trends remain even with sort of the right atmosphere? And we don't know that yet. And I guess lastly, the initial conditions don't really have much of an impact, right? Like all those three runs in length in the nuts show kind of the same thing. And yeah, thanks for your time.
Great, thanks, Ed. Really interesting stuff. So there's a bunch of questions in the chat for you. So in the interest of time, I'll point you to those, and we'll move on to the next talk. So Ian Baxter is up next, talking also about atmospheric circulation and Arctic sea ice. So Ian, let's see if you can share your screen.
Okay, can you see that?
Looks good. Yep.
Thank you. Hi everyone. My name is Ian Baxter, and I'm going to be talking about a very similar set of nudging experiments to that you just saw from Ed. And before I start, I do want to thank the Polar Climate Working Group for their support with these simulations, as well as my advisor, Tsinghua, that you just heard about in the last talk. The only difference really that we're doing with these nudging simulations is we're going to have the same domain and nudging approach, except when we were initially doing these simulations, we were kind of concerned about the initial conditions, and Ed touched on that a bit as well. But one of the ways that we wanted to try and overcome any issues associated with those initial conditions was by doing what we refer to as these perpetual wind nudging simulations. And so for these simulations, what we're doing is we take a single member from the CSM large ensemble on January 1st in the year 2000, and we hold greenhouse gas concentrations fixed at those year 2000 levels. And we run a set of 40 different simulations. And in each different run, we're taking a single year from the reanalysis and we're repeating it for, in most cases, 10 model years. But in the case of the extreme years, we repeat it all the way to 21 model years. And so again, we're doing this nudging from 60 to 90 degrees north in the CSM version 1. And we're nudging to the same reanalysis as you saw from Ed with our interim reanalysis. And one of the things that we saw when we did this was this very strong divergence, and it's fairly symmetrical between the initial starting point at around 5.5 million square kilometers. And so we were fairly confident that there wasn't so much of an influence of the initial conditions, at least in this set of nudging simulations. And so what I'm going to do from here is we're just going to look at the mechanisms connecting our nudged winds with changes in total September sea ice area at the surface. And so to do that, we use this compositing approach where we take the difference between the last 10-year means from the extreme low sea ice cover years in red minus the 10-year means from the extreme high sea ice cover years in blue in panel B over on the right. And so I'm going to start with the composites of atmospheric circulation, and then I'm going to look at changes in sea ice as a response to these winds, and then I'm going to go to how we connect these two processes. And so starting again with those composites of low sea ice cover years minus high sea ice cover years, we find a very consistent pattern because this is what we're nudging to, where we get this figure 8 anticyclonic circulation pattern centered over the central Arctic and extending down over Greenland. And it's this anticyclonic circulation pattern, which is fairly barotropic, that's giving us this large-scale subsidence and warming of the lower atmosphere that you can see in the bottom two panels, zonal mean geopotential height and temperature. And so this is what we think is what we're terming as the optimal wind pattern contributing to enhanced summertime sea ice loss. Next, we'll take this compositing approach and we'll look at sea ice. And so what we're looking at here on the top row is top melt, and then bottom melt, and then lateral melt. And here I split it into June, July, and August. But what we find is that in particular, top melt in July, specifically in the Pacific sector, seems to be contributing the most to whether a year is going to be low sea ice cover year or an extreme high sea ice cover year. Bottom melting seems to play somewhat of a role, but it doesn't correspond quite as well with our extreme years from using total September sea ice area, and takes place more towards the end of the summer. And then the interesting one, I think in contrast to maybe some of the things that were found in Ed's study, is that when we were looking at sea ice mass transport to try and look at sea ice motion and the effects that might have, in particular sea ice export through the Fram Strait and into the North Atlantic, we didn't see too strong of a difference in terms of sea ice movement out of the basin using this sea ice mass transport. Instead, most of the motion was happening kind of in the same region where you get that very strong top melting in July in the Pacific sector. And if you look very closely and squint, some of the vectors here are actually moving more towards Greenland rather than like south. And so another way that we tried to quantify the relative contributions from these different processes is using the thermodynamic versus the dynamic volume tendency terms from the sea ice model. And so looking at the thermodynamic tendency terms in these composites, it shows a very similar pattern to top melting in early summer and bottom melting in late summer, as you would expect. In particular, in July, there's that thermodynamic contribution to top melting in the Pacific sector. Looking at the dynamical tendency terms, it's much harder to see a very clear pattern, but I think if we look at July, we can see evidence for that anticyclonic circulation more so than when we were using the sea ice mass transport vectors, where we can see ice being moved away from the Canadian archipelagos and exposing open ocean in the Beaufort Sea, as well as maybe some export of ice through the Fram Strait, but also maybe, as seen by those vectors, a buildup of ice against the eastern coast of Greenland, as well as a convergence and buildup of sea ice volume within the central Arctic. And when we take the total contribution across the entire basin to total volume change, we find that the thermodynamic contributions seem to account for 90% of the volume change in the difference between our low sea ice years versus high sea ice cover years relative to the dynamical contributions. Though I think it's important to note that I think there are some studies that have shown that sea ice motion is maybe underestimated in GCMs. So it might not be so dominant as we see in these simulations. And then just because we see such a strong influence of thermodynamic processes, we next wanted to look at surface radiative fluxes. And so again, we're using those same composites of low sea ice years minus high sea ice years. And looking at, in these composite maps, the top row is showing downwelling long wave radiation at the surface. And then the bottom two rows are showing short wave fluxes at the surface and then at the top of the atmosphere. And in these simulations, we see a very good correspondence with the reanalysis in terms of radiative fluxes, where we see strong downwelling long wave radiation at the surface in both the nudging simulations and air interim, as well as short wave absorption down at the surface in both the nudging simulations, air interim, and series EBAF. And I've included EBAF here because I think it's interesting, especially when looking at downwelling long wave radiation, where series EBAF shows a very different response in downwelling surface radiation. And we suspect that this is likely due to liquid clouds, or the representation of liquid clouds in both the CSM1 air interim reanalysis and what you get from satellite space measurements that are used in EBAF. And so studies have shown that CSM1 likely underestimates cloud liquid. And so this is maybe leading to a much reduced impact of clouds in these cases. And so to further kind of highlight the kind of muted effect of clouds, we use the same APRP method that you saw earlier from Andrew to decompose, in this case, short wave feedbacks into the surface versus the cloud and versus the non-cloud atmospheric components. And we see a very dominant influence of just changes in surface albedo relative to changes in clouds, where the surface albedo changes in the first year of these nudging simulations is contributing about 12 watts per square meter over here on the right to JJA mean shortwave absorption. And this increases all the way up until about the 13th year in these simulations, where it kind of tops out at about 25 watts per square meter. Clouds, on the other hand, are contributing very little, so about a little less than 1 watt per square meter. And they're actually positive, so they're in June and July, so they're contributing to more shortwave absorption in those 2 months. And this might speak to the lack of liquid in these clouds and their muted effect. Then just the last thing that we do is we wanted to compare with the CSM pre-industrial control simulation to kind of gauge what was coming from the model, what was coming from our wind nudging. And so we take the same approach here, where we take, in this case, we've done non-overlapping running 10-year means, and we've taken the low sea ice periods minus the high sea ice periods, and we've done the composites there. And so we find a very similar pattern actually in the CSM pre-industrial control simulation, where we have that figure 8 barotropic anticyclonic pattern with one lobe centered over the central Arctic and then extending down over Greenland. The one kind of subtle difference I would say is that that Greenland extension is kind of shifted more towards the eastern side of Greenland relative to in the nudging simulations and the reanalysis, where it's on the western side. But in the case of the most extreme period that we found in the CSM pre-industrial control simulation for sea ice loss, we find a very similar pattern with this figure 8 anticyclone, as well as in terms of the magnitude here as well. And so just to kind of leave you with some of the, I think, the major findings from these perpetual wind nudging simulations is that the optimal wind pattern for enhanced sea ice melting seems to be this figure-8 barotropic anticyclonic pattern. And the contribution from this wind pattern seems to be primarily thermodynamic. So substance-driven warming of the lower atmosphere, reducing sea ice cover, and then inducing this ice albedo feedback rather than dynamic, which I'm kind of using as like indicative of not so much sea ice export out to the North Atlantic. It also seems that these surface albedo feedbacks take actually quite a while to really saturate. And so it seems about 13 years. And so if there are successive years or more frequent years of this anticyclonic high pressure system over the Arctic, it could lead to enhanced sea ice loss. And we think maybe this is what played a role from 2007 leading up to the record minimum in 2012, where you had maybe 5 out of the 6 years with this high pressure over the Arctic. And then just lastly, we're going forward, we're working on applying this to CSM2, and I think there will be major changes. As Marika said, the models are quite different. And I'd be interested, especially in terms of the changes in clouds. And so with that, I just want to say thank you. And thank you especially to the Polar Climate Working Group for helping us with these simulations.
Thanks, Ian. It's really interesting stuff. And I think these nudged wind runs are just so valuable. So yeah, it'll be interesting to see what you find at CESM too. So I think we're going to move on because again, we have time limitations, but there's some interesting questions in the chat for you. And so please address them there. And so we're going to move on to a talk from Erica Rosenblum. There you are.
Hi. Can you hear me?
Yep, I can hear you well. Talking about surface salinity in the Arctic. So let's see if you can.
Is that working?
That looks good.
Okay, great. I'm just gonna like hide my face so I don't distract myself. Okay, hi everyone. Oh, no, it popped up, that's fine. So today I'll talk a little bit about work that's just been published at GRL at the end of last year, looking at surface salinity in the models and observations under changing sea ice cover in the Canada Basin in 1970s and in the 2000s. Okay, so this is the main problem we're looking at that motivated this work. So this is showing the climatological salinity as a function of depth in the observations shown in the dashed line. So salty at depth, and then as you move to the surface, it's progressively fresher. And then these lines are showing the ice ocean component of all of the climate models used in CMIT-5, including NCAR here in blue, and the bias away from those observations. So at depth, all the models are doing quite well. And then as you move to the surface, you start to see biases. And in particular, I want to point out, if you go right up to the surface, all of these models show that it's a bit saltier than what's observed, including CSM here in the light blue. Okay, so there's a few possibilities that could be causing this bias. Oh, sorry, and I wanted to point out that why do we care about surface salinity? Well, that's going to impact the stratification, and that has a really big impact on the vertical transport of heat and nutrients, and that's going to impact the sea ice cover. So going back to different hypotheses of what could be wrong. So one possibility, it could be related to sea ice cover or other sources of freshwater input, and that there could not be perhaps there's not enough freshwater input each year or over the decades. Another possibility could be related to the vertical mixing, so the ocean component of the model and what happens to that freshwater over time. So previous studies have looked at this just using simulations to look at different processes that are involved. And then there's other studies like this one that just take a climatological average of the observations and compare it to the models and say, is this working, yes or no? So here we're going to kind of use a melded approach where we're going to be looking at how seasonal processes are changing on decadal timescales in the models and observations to try to see if the observations can tell us about what the model might be missing. Okay, so that's generally pretty difficult to do because we usually don't have annual, like a full year of data in the Arctic Ocean because sea ice is a tricky thing, especially over the last few decades. But there's one place, and that's the Canada Basin, that has a few really unique data sets that we're able to use here. So the first one comes from the Arctic Ice Dynamics Joint Experiment, or AJEX for short. So this program happened over the course of 1 year, 1975 to 1976. Scientists were living on the sea ice in these ice camps for an entire year. So this is showing the estimated September sea ice cover from satellite observations in white. And then the blue dots are showing the locations of these 4 ice camps as the ice flow kind of drifted along during that year. Okay, fast forward a few decades, and now we have these fantastic ice tethered profilers. So these are automated instruments that are frozen into the ice flow. They're attached to an 800-meter wire with an instrument running up and down it 2 to 3 times a day, collecting measurements of temperature and salinity, just like an AJEX. And a lot of these have been deployed in similar regions as the AJEX ice camps. So there have been a number of studies that compare these 2 data sets and ask, well, how has the ocean changed over the last several decades? So this is one example of that, showing salinity as a function of depth in 1975 in blue and the 2000s in red. And if you go down the bottom, you see they're quite similar at depth, but as you move to the surface, recent years are indicating a much fresher surface layer. Okay, so we want to try to, again, look and try to understand, using these 2 data sets, what's going on with the models and why do they tend to be too salty at the surface? Are they simulating the seasonal changes? Are they simulating these decadal changes? So we're going to be using ITP and AJEX data for the observations, and we're going to be comparing this to 30 simulations from CESM1 and 50 simulations of CESM2, and we'll also look at some sea ice data from the NSIDC, looking at ice concentration and biomass. Okay, so first we just take our data set and see if we find what others have seen before. So this is showing I think this is the August average salinity profile in 1975 in blue and the 2000s in red. And consistent with previous studies, we see they're quite similar at depth, but at the surface, we're seeing that very fresh surface layer. And that's, as you can see in recent years, that means a more stratified ocean, and so big implications for the vertical transport of heat, energy, and nutrients. So our first question we wanted to ask is, do the climate models capture that change? Okay, so this is showing, so what we did is we took a basin average over the Canada Basin and then an ensemble mean for 1970 all the way to 2020, where each line here, so 1970 in blue, 2020 in red, so each line is indicating 1 year of that basin ensemble mean in CESM1 and CESM2. And as you can see, in contrast to the observations, you're just seeing a gradual freshening over those 50 years, in contrast to the observations where you get quite a bit of fresh water at the surface. And we can focus in on August. This is true of all months, but I'll just focus on August because that happens to be the freshest month of the year. And if you look at all of the available observations in the 2000s and every grid point of every simulation from CSM1 in black and CSM2 in purple, you see this is statistically significant difference. So this can't be explained by internal variability or regional variability. So this is the main question we want to try to focus on answering. Why does there appear to be fresh water missing from the surface? Why is it too salty? So we look at a few different possibilities and we try to split them up in terms of freshwater input and vertical mixing in the hopes that this will help us figure out, is the problem more related to the atmosphere or sea ice processes, or is it really in the ocean component of the model? So we're going to look at, is there enough sea ice, sea ice melt, or other processes related to freshwater input, or how it's vertically mixed. Okay, so first we want to ask, well, is there enough seasonal simulated freshwater input on seasonal scales? So to look at that, we examine the sea ice concentration that corresponds to the ocean observations. So we have 1975 in blue and the 2000s in red, and then over the same time periods in CSM 1 and 2. And then we also do the same thing for effective ice thickness, so that sea ice volume per unit area from biomass in CSM 1 and 2 over 1979 to 2018. And qualitatively, we see some differences, but a lot of similarities, namely a downward trend over all months. But we want to try to be a bit more quantitative than that. So what we do is we look for each grid box of each year. We just look at the difference in sea ice thickness between May and September, so the sea ice season, and ask what's the difference in these three models. And we find that they're actually quite consistent when looking over that distribution. And so this suggests that probably sea ice melt is not the problem here. This isn't causing the missing fresh water at the surface. But we know that there's other sources of fresh water besides sea ice melt. There's also river runoff and precipitation. And so to try to get at that question of, is there enough freshwater input being added each year over the course of these decades so that there would be enough freshwater at the surface, we turn to the seasonal evolution of salinity profiles. So to give you an example of how we do this, this is showing the salinity profile evolution just from one model. So you have June, July, and August. And as you move through the melt season, you're progressively fresher at the surface. And what you can do, for example, is ask, well, how much fresh water has been stored or added to the ocean surface since May by the time August comes around? And what you can do is you can make a simple estimate where you say, well, I'm going to assume any freshwater or any change, I'm going to attribute that to freshwater input at the surface. And I know that freshwater input is going to be lighter or less dense than the main mixed layer salinity. And so given that those assumptions, I can apply a conservation of mass and salt between the surface and where those two profiles intersect. And that will allow me to back up an expression for the freshwater input that would be necessary to explain that transition from a May mixed layer salinity to the eventual August salinity profile. And this is very similar to a freshwater content term used in other studies, but instead of a reference salinity of 34.8, we're using the May mixed layer salinity. So this is just telling us the freshwater input that's occurring on seasonal timescales near the surface. Okay, so we take that expression and we apply it to every observation, every grid point of the simulations and look at the average. And this is what we find. So we have observations on the top, 1975 in blue and the 2000s in red. And then again, that in the simulation CESM 1 and 2 from 1970 in blue to 2020 in red. And focusing just on the 2000s, we see there's a lot of similarities there. There's a general increase over the melt season, and it gets between 1 and 2 meters of fresh water. But again, we want to be quantitative, so consistent with what we did before, we focus on the month of August, and we look at every grid point of every simulation and all of the observations and look at that distribution, which is shown here. So observations are in red and CSM 1 in black, CSM 2 in purple. And we see there's a lot of overlapping grid points here. So that suggests this is much more consistent. On average, there's a bit more freshwater input in the models than in observations, but that could not explain why the surface is too salty because there's more than enough freshwater input going into the ocean in the models. So this does not seem to be the source of this missing freshwater bias either. Okay, but even if you have about the right amount of freshwater input, this can be stored or vertically distributed in the ocean differently. So here's an example of that. We have profiles from the observations in a climate model, just one example. And the area under this curve is directly related to that seasonal freshwater storage term. So you can see the areas are quite similar, but in the observations here, it's stored much closer to the surface. And so that results in more seasonal freshening. So we want to try to quantify that difference. And to do that, we take that same term, that seasonal freshwater content term, and we split it up into 10 components where we set each term equal to 10% of the total freshwater content. And then we solve for the bounds, which will indicate where is 10%, 20%, 30%, 40%, all the way down to 100% of the freshwater stored as indicated by these gray bars. So we do this, we take this, this expression and we apply it to every observation and every grid point of every simulation. And this is the average shown from June to December. And right away, you can see that the observations across these months are showing that the freshwater is stored much closer to the surface than what's seen in the models. And again, we want to quantify this. So we just pick out the point where 90% of the freshwater is contained, the depth where 90% of the freshwater is contained. And this is showing the distribution we get again in August for all of the observations in red, and then all of the grid points of all the simulations in CSM1 and CSM2 in black and purple. And as you can see, there's a statistically significant difference between the two. And this suggests that this is a source of the bias. Part of the problem here is that the freshwater, even though there seems to be enough freshwater being added each season, it's being unrealistically transported at depth. And so that's causing the surface to be less saltier than it would otherwise. And what I wanted, so that was just a focus of the 2000s. I want to jump back and just add one more layer to this and bring in 1975. So same plot as before, where you have the observation, CSM1 and CSM2, showing the distribution of that fresh water. but 1975 at the top in the 2000s. And as you can see in the observations, there's this very clear shift where that fresh water is stored quite deep in the 70s, down to 25 meters or so. And then there's this shift where recent years that fresh water is concentrated closer to the surface. And we see that the climate models are not able to simulate that change. Instead, they continue to show vertical extent of that freshwater mixing at a depth that's much more consistent with the 1970s than what's seen currently. Okay, so I'll just quickly summarize. We looked at simulations from CSM 1 and 2 and compared them to ocean observations from 1975 and the 2000s in the Canada Basin. We found that in contrast to the observations, the models were not able to simulate surface freshening that is dramatic as what's been seen in observations, and that this is probably not due to biases related to sea ice evolution or a freshwater input, but that it is in part related to the freshwater unrealistically transporting that freshwater deeper than what's observed. And then I'll just leave up, these are some recent publications related to this work. Thanks.
Thanks, Erica. It's really great to see some ocean analysis being done with CESM. So pointing out the biases there. So I think, again, as with everyone else, I think we're just committed to questions in the chat at this point, and there are a couple questions there for you. So if you could address them there, and we will move on to the next talk. So thanks, Erica. So Jed Linetsky, who is also talking about freshwater and Davis Strait freshwater fluxes. So Jed, if you can share your screen.
Does that look okay to everyone?
It looks great. Yep.
Okay, perfect. So yeah, so thanks so much. For those of you who don't know me, my name is Jed Linetsky, and I'm a PhD student at CU Boulder. And I'm going to be talking about understanding Davis Strait freshwater flux variability using models and observations. Sorry about that. And this is work I'm doing with my advisor, Alexandra Yon, Paul Myers at the University of Alberta, and Craig Lee at the University of Washington. So why study the Davis Strait? A significant portion of the Arctic water outflow into the North Atlantic travels through the Davis Strait, and that outflow has really important implications for global climate and the Atlantic meridional overturning circulation. At the same time, we have a limited observational record. So we've only had moorings in the Davis Strait from 2003 to 2015. And so this limited observational record gives us a really nice opportunity to try to use models to try to find the drivers of volume, freshwater, and water mass fluxes through the Davis Strait. And the end goal is to see if we can develop statistical methods to extend the observational record and to better allow us to understand the processes at play in this region. So just on the right, we can see the observational record of freshwater fluxes in blue and volume transports in orange. And really the key point here is that we can see variability at monthly, interannual, and decadal timescales that we're really trying to unpack. So the data that we're using is two CSM2 hindcast simulations. One at a 1 degree resolution and one at a 1/10 degree resolution. And so both of these models are coupled ice ocean models, and with a forced atmosphere from JRA 55. And then we also validate these hindcasts with observations from the Davis Strait mooring array. And just to give ourselves some quick spatial context, we can see the Davis Strait in black. And then what this map is showing is the vertically integrated freshwater column in the 1 degree hindcast. So we can see in the Arctic Ocean and Canadian Arctic Archipelago, in the green is fresher compared to the Arctic Ocean, which is saltier in the yellow. So the first question is kind of how well do fluxes from these hindcasts actually match the observations? So when we're looking at freshwater fluxes, we can see that both the 1/10 degree and 1 degree model match the observations in black relatively well in terms of both mean state and variability, which is good. But then the volume transports become a little more complicated. So both models can match the volume transport mean state relatively well, although there is kind of a weaker northward bias in the higher resolution 1 degree hindcast. And then also the 1 degree hindcast in red significantly underestimates the overall variability in the volume transports. So this is just something to keep in mind. And then also the 1/10 degree hindcast can actually capture Davis Strait flow reversals, which is a phenomenon that's been observed in the observational record a few times, and that's where the Davis Strait flow, which is normally southward, as we can see, will actually become northward. And so the 1/10 degree hindcast can actually capture this phenomenon, but it overestimates it and happens a bit too frequently compared to the observational record. And then we're also interested in the water mass structure in these models as well. So what we're seeing here is in the top row is cross sections of temperature on the left and salinity on the right of the Davis Strait. And we can see at depth on the eastern side of the Davis Strait, so on the right, we can see this warmer, saltier core of Atlantic water. And then at the surface, a fresher, colder core of Arctic water. And the key point here is that the high resolution hindcast on the bottom row can capture this, can capture the structure can horizontally capture this structure. Whereas in the 1 degree hindcast in the middle row, we really only see the vertical stratification, and we don't actually see any of the horizontal. We don't really see much of the horizontal structure in these water masses. So yeah, so really this is very preliminary work at the moment, and really what we're focused on right now is seeing how well the sea surface height gradient corresponds, or the sea surface height field in these models corresponds to fluxes to volume, freshwater, and Arctic and water mass fluxes through the Davis Strait. So the first plot I'm going to show is correlations between sea surface height anomalies and Davis Strait volume flux outflow anomalies. So this is the amount of water leaving the strait only. And we can see, as we'd expect, a pretty strong sea surface height gradient between the Canadian Arctic archipelago in red, and then Baffin Bay in the North Atlantic in blue. And then so then if we take regional averages of sea surface height anomalies in the Canadian Arctic archipelago, and then also in Baffin Bay, and subtract them, we can approximate a sea surface height gradient anomaly. And this sea surface height gradient anomaly on 6 month, if we do a 6 month smooth of the data, can explain 82% of the volume flux variability and 55% of the freshwater flux variability. And then looking at the high resolution model, kind of interesting differences appear. So this is the same sea surface height anomaly correlated with the volume flux outflow anomaly. And interestingly, the sea surface height gradient is much weaker. So we don't really see the same level of strong gradient, but between the Canadian Arctic archipelago and Baffin Bay in the North Atlantic. We do, however, see a correlation maximum. This should be a little farther north. Sorry about that. But yeah, in the Labrador Current region. And so then, if we just take a regional average of sea surface height anomalies in that region, we can explain 49% of the volume flux anomaly and 34% of the freshwater flux anomaly. So we're still kind of interested in trying to figure out why, just to go back a second, this gradient is much weaker. And one potential explanation, two ideas we have that would be great to hear thoughts on if any of you have it, is that one, just in the high resolution model, the Canadian Arctic archipelago and the channels are much more realistic. So that could be kind of complicating the gradient structure. And then also in this model it's a 1/10 degree resolution, so it's eddy resolving. So there could be other ocean processes at play that are influencing the volume flux beyond just kind of this basin-wide sea surface height gradient. So just something to keep in mind. So then, as I mentioned earlier, we're also interested in the Arctic water flux through the Davis Strait because it's in this water mass where the vast majority of the fresh water is contained. So once again, if we take correlate sea surface height anomalies with Arctic water flux anomalies, we can once again see this very strong gradient, but this time it's concentrated on the western side or the western region of Baffin Bay and the Canadian Arctic archipelago. Then we also see once again this region of correlation, high correlation in the Labrador Current. So then once again, if we take the gradient, but if we do a regional average and then a gradient, and then subtract the two regions from each other, we can explain 44% of the Arctic water flux through the Davis Strait. So just some key points, both the 1 and 1/10 degree CSM2 hindcast can capture Davis Strait volume and freshwater flux variability. Only the 1/10 degree hindcast can resolve water masses. And we think this is mostly due to just horizontal resolution, the difference in horizontal resolution between the two models. And then sea surface height gradient anomalies between the Canadian Arctic archipelago and Baffin Bay can explain 82% of Davis Strait volume flux anomalies and 55% of freshwater flux anomalies in the 1 degree hindcast. And then in the high resolution 1/10 degree hindcast, SSH anomalies along the Labrador Current can explain 49% of volume flux variability and 34% of freshwater flux variability. And then additionally, sea surface height gradient anomalies between Western Baffin Bay and the Labrador Current can explain 44% of Arctic water flux variability. So just some next steps. Our next steps are really just to further investigate the differences and to further investigate these model differences, as well as the sources of water mass variability in the high resolution hindcast. And then we'd also like to apply the sea surface height method to observations in the hopes of extending the observational record. So yeah, so I'm happy to take any questions. My email is listed below, and thanks so much for listening.
Thanks, Jed. That was really interesting. So, and again, good to see ocean analysis being done with the model because we often seem to overlook the Arctic Ocean. So that's great. So again, I'll point you to the chat. I kind of figure we're committed to the questions in the chat at this point. So please put your questions for Jed into the chat. And we'll move on to the next talk, which is from Robin Clancy. Great. And yeah, if you can share your screen.
Is that looking okay?
That looks good.
Awesome, cool, thank you. Right, yeah, so I'm Robin Clancy from the University of Washington. Yeah, and I'm going to talk about how cyclones affect sea ice and how this is going to change in the future under global warming. I'm going to kind of rush through the first half of my talk, which is more based on present day, how cyclones affect sea ice. It's a bit more weather focused, so then I can move on to the more kind of climate related stuff in the second half. So if you want to hear more details about kind of the present day stuff and also maybe some more about the structure of atmospheric cyclones, and some more about the thermodynamics of how they influence sea ice. That's in this paper here. Yeah, if you want more details. So in the past, like a lot of the research about cyclones and sea ice has kind of come down to the question of if cyclones cause an increase or decrease in sea ice, kind of on the whole in terms of sea ice area. And so you've got papers like these ones on the left that suggest it typically causes a reduction in sea ice. This one in the middle that says, depending on how you kind of sample your cyclones and find out where your cyclones are, you can get entirely opposite results. And you got these papers which generally say you probably get an increase in sea ice with cyclones. So definitely no kind of consensus, but mostly papers have been kind of looking big picture. Do they cause a net increase in sea ice area or decrease in sea ice area? And so what we've gone on to do is basically look at not so much in total sea ice area, but more in terms of the patterns of sea ice concentration and thickness. What's the influence of Arctic cyclones? So yeah, the questions we'll address really are first trying to get to present day how cyclones affect sea ice. Is there an increase, a decrease? Is there some kind of pattern to this? Second, we'll get into the processes which drive this sea ice response. I'm going to focus on the dynamics, which end up being the key process that determine the pattern of response. But there's a lot of thermodynamics going on as well, which kind of have a secondary role. And then we'll look into how this would change in the future. Is the sea ice going to be more sensitive or less sensitive to Arctic cyclones in the future, and what are the implications of that? So to start with the kind of present day stuff, we're looking at 1985 to 2016. We've got these Arctic cyclone tracks, which we select the 25% most intense ones. So you can see the kind of spatial distributions of these Arctic cyclones in each season here in the figure. So we're looking at fairly strong Arctic cyclones. Using satellite sea ice concentration data, and then we'll also use the CES5 sea ice model, which we forced with JRA 55 reanalysis for the same time period, to get a bit more detail on the mechanisms. And the method we'll be using is pretty much this throughout a lot of this talk. So the idea is that we composite the effects of cyclones by regridding anomalies in various variables onto this kind of cyclone-centered grid. So this red star in the center is a cyclone. And then you can see you've got north at the top, south at the bottom. And then these grid cells is a grid of basically distances and directions away from a cyclone. So these anomalies on the left, for example, would end up looking like this in this new regridded projection. So if we do this a lot of times and take the average over kind of several thousand cyclones that we've got in our collection, you get the average response of these variables to cyclones. So yeah, without further ado, the effect of these cyclones, we're going to start with on sea ice concentration. So what I'm plotting here is the 5-day before cyclone to 5-day after a cyclone anomaly in sea ice concentration change. It's kind of a lot of words. Basically, where you see this bluey green color, that means you're increasing your sea ice more than normal. And when you see this kind of browny color, you're getting less sea ice than normal. So you're decreasing sea ice faster than normal, or increasing it slower is also another interpretation depending on the season. So blue more sea ice, brown less sea ice, basically. So this top row here is from observations, and you can see this kind of east-west sort of dipole that happens, where to the east of cyclones, you get reduced sea ice concentration, and to the west of cyclones, you get increased sea ice concentration. And then, so in this second row, what we've done is we've taken the CES5 model, forced it with reanalysis, and done the same kind of compositing. And you can see that you get the exact same almost pattern of east and west differences in sea ice response to cyclones. So this is pretty cool. I think this shows that CES5 is doing a fairly good job of representing how the sea ice should be responding to cyclones. There's obviously a chance it's doing it for the wrong reasons, but I think it's pretty encouraging. And it allows us to do some other cool things. Like, for example, we can now get a good idea of what the thickness is doing of this sea ice in response to cyclones. And again, we get this kind of east-west dipole, loss of sea ice to the east, gain of sea ice to the west in CES5. So one more way of kind of looking at this pattern, if we take some measure of the strength of this east-west dipole and plot it at each grid cell, so we say, is this grid cell gaining more sea ice when it's to the west of a cyclone than when it's to the east of a cyclone, it loses sea ice? So these green little patches, basically when they're about 20%, says you are gaining 20% more sea ice when this grid cell is to the west of a cyclone compared to when it's to the east. And in each season, you can see, basically it's pretty consistent. Almost everywhere you're seeing these green colors, which means this dipole pattern is pretty dominant throughout the Arctic. Where it's strongest though, however, is between these kind of red and purple lines, and those represent the marginal ice zone contours in the climatology, so 15 to 80% sea ice concentration. So basically this east-west pattern of response of sea ice to cyclones, is most prominent in the marginal ice zone. And I'm not showing it here, but you get a similar pattern for sea ice thickness, and these patterns are really well recreated by size 5 as well. So that's encouraging that size 5 again can recreate these patterns too. And so the other thing that SICE is allowing us to do is to break this down into its dynamic and thermodynamic components. And so we've got this for sea ice concentration here, and for sea ice thickness, we only show the thermodynamic component here. So the dynamic component, because the thermodynamic component is super small, basically negligible. And what we basically see is that while the sea ice concentration has some influence on thermodynamics, it doesn't really have this east-west dipole, maybe slightly in some seasons. But for both concentration and thickness, the east-west dipole of response of sea ice to cyclones is dominated by dynamics. So it's really dynamics causing the dipole of more sea ice to the west and less sea ice to the east of cyclones. And so just to kind of get at this mechanism, we break this down a bit more, but to put it simply, if you look at the winds that we've got here from ERA5 reanalysis that we plot, you can kind of understand what's going on in that sea ice typically has kind of a north-south gradient or a south to north gradient in either thickness or concentration. And so if you put this kind of cyclonic circulation on top of it and kind of advect it cyclonically, you're going to be moving ice up gradient, I guess is how you'd say it, to the east and down gradient to the right. So this is going to result in a net divergence of sea ice here and convergence here. And that's essentially the mechanism, which is kind of driving this thermodynamic gain of sea ice to one side and loss to the other. Yeah, so we'll get into that more in a bit. So in terms of what we can tell from kind of the present day, we've got this gain of sea ice to the west of cyclones, loss of sea ice to the east, which is primarily driven by dynamics, although there's some thermodynamics as well, which I've not mentioned much, and yeah, I'm happy to talk about. Okay, so moving into the future, we're going to try to figure out how this might change, whether the ice will become more or less sensitive to cyclones, and why that is. And so there's a lot of competing hypotheses out there. People have talked about this a little bit. You could imagine you would get greater drift speeds due to the ice being more broken up and mobile. You might have kind of a warmer ocean, so you can get more influence from the ocean when the sea ice kind of mixes up the ocean heat. And then there's this idea of maybe when more of the ocean is exposed, you're maybe going to get more sensitivity to the atmosphere because you can absorb more sunlight and things. So yeah, there's a lot of hypotheses out there, but I don't think any of them are really getting at what the true answer is. So we're going to use the CSM1 large ensemble to look into how the effects of cyclones is going to change in the future. We already know that the sea ice model in CSM is pretty good at representing these processes because it's the size 5 model that we used in the previous part of the talk. So we're going to use these tracks from Johnny Day that he provided. So we didn't do the tracking, but someone has tracked all the cyclones in the CSM1 large ensemble. And we're taking just a snapshot of a few years going from in the past to kind of far into the 21st century and looking at how the effects are going to change. And again, we're using the same kind of compositing method on this cyclone-centered grid to do this. Okay, so for each of these plots, I'm going to have kind of 1991 at the top going through to 2074 in the bottom. And so on the left here, I've got the sea ice thickness change, and you can see that compared to 1991, the future years have a much smaller pattern of sea ice thickness response to cyclones in the future. So I don't know if any of you were expecting this when presented with kind of this question here, but this kind of surprised us that in fact there's such a large reduction in the influences of cyclones on kind of local sea ice thickness. In contrast, if you look at the sea ice concentration change, there's some differences going on year to year, but at least into like the early to mid 21st century, it's a relatively constant pattern compared to the sea ice thickness change. Going out into 2074, particularly in summer and fall, then you don't see that so much. This is when you're nearing very little ice at all in CSM1 large ensembles. So it's not surprising maybe that you're getting some strange things going on there. And you do get some slight increases in the influence on sea ice concentration, yeah, like later into the 21st century. I don't think I'll be talking about that much, but I'm happy to answer questions on it as well. Okay, so this previous plot is the sea ice thickness and concentration response. And now we're going to put on the next slide the concentration and thickness response that we can attribute directly to dynamics. So this is thickness and concentration, and this is the dynamic response. And you can see that the pattern is pretty much recreated by the dynamic response, as is the relatively constant magnitude of the sea ice concentration, but declining magnitude of the sea ice thickness. So basically what this is saying is if we can understand how the sea ice dynamics are working here and why they're creating this pattern and why this pattern is changing over time for sea ice thickness, but not concentration, then we can kind of understand why these changes are happening for thickness and concentration in general. And so our mechanism really comes down to these meridional gradients in sea ice thickness and concentration. So we've got this kind of north-south gradient on the left here, sea ice thickness plotted for each year. Yeah, so positive gradients, meaning more sea ice to the north than to the south, are here in kind of orangey brown. I've kind of outlined them in this black contour, and negative gradients here outlined in this purple contour. And you can see that for thickness, particularly the regions of positive gradient really kind of diminish in both spatial extent and kind of magnitude over time, leaving actually just largely the areas of negative gradients in sea ice thickness remaining in some seasons. For concentration, the response is very different. In fact, out until at least 2034, and at least in winter and spring until 2074, the magnitudes and kind of spatial extents of the gradients remain pretty constant again. This might be sounding familiar compared to some previous graphs, kind of a decline in sea ice thickness gradient, but a constant sea ice concentration gradient. So how is this important? Okay, so we're going to keep these black and purple contours of positive and negative gradients on the next plots, but we're also going to plot this east-west difference in, well, this east-west dipole strength as well. And what you'll see is the east-west dipole strength at each of these locations basically matches very well with where we've got these kind of different positive and negative meridional gradients. And so it's not perfect because obviously there's kind of zonal gradients in sea ice that are going to play a factor, but generally you get this east-west pattern with gain to the west and loss to the east when you've got positive gradients in sea ice thickness or concentration. But you actually get like a negative pattern, so like the opposite of this dipole, basically, where you have a negative gradient in sea ice concentration or thickness. So all this is to say that these, these changing gradients in sea ice concentration and thickness over time are going to determine how much of this east versus west pattern you get. And into the future, by 2034, particularly for sea ice thickness, you've not got many regions of positive gradient, but you've still got some regions of negative gradient. These positive and negative like east-west dipoles start to cancel each other out and result in a very minimal effect of cyclones on sea ice. So this all comes down really to these sea ice loss patterns. So for the CSM1 large ensemble going from 1991 to 2023, you can see that for sea ice thickness, you lose the most ice in the central Arctic, where the ice is thickest. But for sea ice concentration, you lose the most ice in the marginal ice zone. And that's kind of what's causing this difference in the pattern of loss of gradients. Losing sea ice near the central Arctic will give you a reduced gradient, north-south gradient in sea ice, whereas losing around the marginal ice zone doesn't quite have the same effect. So that explains why the sea ice concentration doesn't show the response to cyclones, doesn't show the same decline as sea ice thickness. This is only one model. I'm going to quickly show this. This is very much a work in progress, but we've been checking this out in CMIP 6, and it seems like a pretty consistent feature. that the thicker sea ice is that what gets lost most. These different colors are CMIP6 models. This black is the large ensemble. So the larger starting thickness, the more sea ice loss you get for an individual grid cell. So yeah, we're still working on this. This is a bit of a teaser of some future work. And so to kind of finish off, I kind of want to make this into maybe a bigger statement than just about cyclones, in that because this all comes down to the sea ice thickness and concentration gradients, it should apply to any other synoptic system and pattern of kind of wind influence on sea ice. So I've got similar plots here for anticyclones. You can see you get a declining effect of anticyclones on sea ice thickness, but a relatively constant effect of anticyclones on sea ice concentration. So the implications are maybe that regional variability of sea ice thickness might be reduced by this mechanism by having kind of smaller gradients in your thickness, but you won't see this so much in concentration. So this is just the summary slide. Basically, you get this east-west dipole in how cyclones affect sea ice concentration and thickness, primarily happening in the MIZ, Yuvan due to that being where they have the biggest gradients in concentration and thickness. This is primarily thermodynamics that drives this pattern, but there's some other things going on too that I haven't talked about, but I can do. And this pattern, so the sea ice is going to be less sensitive to the cyclones in the future in terms of sea ice thickness, but largely constant sea ice concentration. So I've done this little diagram to show the changing gradient of sea ice thickness and how that interacts with the motion. And I think that's the way to think about this. So that's all I've got. Thanks for listening.
Great, thanks, Robin. Really interesting work. So to be consistent, I don't want it, since you're the, well, actually, I think I'm going to check if Petra Heil is here because she is on the agenda. It doesn't look like she's here, but she did let us know that she might not be able to make it. And so it looks like she wasn't able to make it. And so we won't have Petra's talk, but in the interest of fairness for all the speakers, I'm going to have people put questions into the chat for you as well. So please, people, ask your questions there for Robin. So we do have a little bit of time for discussion, and I don't know if everybody is kind of zoomed out. I will say that we have time tomorrow for discussion where we will have breakout groups, so it'll kind of enable a more effective conversation among smaller groups. But just maybe as some teaser topics to get people thinking overnight to come to the discussion tomorrow, and also if people have burning thoughts that they want to bring up right now. A few of the things that we would like to discuss tomorrow are developments for CESM3 or developments after CESM3, since we have this fairly short time frame to get a model ready for CESM3, which is by summer of next year, so just a little bit over a year. But so kind of developments towards CESM3 and after CESM3. Also data assimilation capabilities and whether there's an interest in having new cryospheric data sets, particularly satellite data like ICESat-2 data, as part of what DART supports in their sea ice data assimilation capabilities. So I'd love to hear people's thoughts on that. And I think there's many people that are doing more with data assimilation than I am and have probably better insights on this. And then another topic is simulations that are of interest. So we've heard today about some quite unique simulations, for example, with nudged winds to look at the role of wind variability on Arctic sea ice. And we do have computing resources under the Polar Climate Working Group. And so some ideas about particular experiments people might like to see as we move to CESM3, and those kinds of questions, and also simulation capabilities. So not just model physics, but things like a nudged wind capability within the context of CESM3. So those were some of the discussion topics that we wanted to address tomorrow. And these are true for land ice, but I mean for sea ice, but also or sea ice and polar climate, but also land ice related research. So similarly kind of addressing both of those working groups. So I don't know if anyone has any thoughts they want to bring up right now on those questions, or if people would prefer to end early. So I'm trying to keep an eye on the chat too, because and Ed, you turned your camera on. Yay, if people want to turn their cameras on, that might, I won't force you, but it'd be nice to see some faces.
But I have a student master's defense in 23 minutes and I have to go and read her thesis. But my ears perked up when you're talking about proposed simulations. But I think it'd be great to talk about this tomorrow.
Yeah, okay. Yeah, I mean, it's definitely more effective to have small breakout groups than a big group trying to chat with each other. So we were planning to do that. So I get that you have to read a thesis, so.
I know we haven't talked about this today, but I was also very curious about the ocean wave sea ice interaction for CSM3. And I know that was highlighted in like the brown or kind of yellowy color. So I don't know if you could give us any more details maybe tomorrow on that.
Well, I think, so Dave actually knows more than I do about what's happening with the wave watch coupling. So maybe I'll see if he has something to add to this.
I think a lot of it is just a technical issue right now, because all of Letty's work has been in the context of CSM1 or, early on. And so we have a new coupling infrastructure, and there's a lot of really problematic things that we have to deal with. The other thing is there's actually somewhat of a political issue with this because WaveWatch is a NOAA product, and so we're trying to work with NOAA right now to utilize that, and and then we want to have a unified cap between the NOAA model and the NCAR model. Anyway, there's a lot of issues that are delaying this. So that's, I think, part of the reason, at least, why Marika put it in as sort of longer term.
Yeah, I mean, they want this for MOM. They want WaveWatch working within the context of MOM as well. So we're not the only working group that has an interest in having wave as part of the model, basically. But I have been listening over the months to conversations that are mostly between Dave and Mariana, who's the head of our software engineering group. And it just seems like, it's progress is slower than
right.
I think anyone would like. And so that's why I put it in orange, because I don't want to promise something that might just take longer than we all expect.
I mean, the wave ocean interaction is already in there, and that will continue, but it's the wave sea ice part of it that's a bit more delayed. And, another interesting conundrum, I've talked to Baylor Fox Kemper a bit about this, is the expense of WaveWatch. And so can we really afford to run 1 degree WaveWatch globally? And so Baylor's been working with his group a lot on sort of a more theoretical wave model that's a little bit cheaper. And so, yeah, there's a lot of interesting developments with that.
I'll also just say on the list of things that we are hoping to include in CESM3, many of those we haven't tested yet within a coupled model context. And so what we actually end up with is going to depend on what coupled simulations look like with these, these improvements. So yeah, so there's still quite a bit of work to do before we, land on this is what's in CESM 3. And I think that's true for all the working groups at this point. So does anyone have other things they want to bring up or other things they want to make sure get discussed tomorrow during our breakout discussions? Or is everybody ready to go read a master's thesis?
Marika, your comment on testing reminded me, I'd be curious to know about plans for testing the new snow physics and what kind of what the plans are there.
Yeah, so the plan is to do coupled model experiments. Again, this is kind of on Dave's plate. He's got a pretty full plate. And I think, and Lorenzo's also had some interest in looking at these in forced simulations. So ice ocean simulations. But we'll be using, I think, to start, what's available in CEIS 6 with the parameters that are used in CEIS 6 and assessing the coupled model solutions there, and starting with a pre-industrial climate for the fully coupled runs. And then looking at how it affects the climate system and possibly making adjustments based on how it's affecting the coupled climate. Yeah, does that help, David, or is there something more specific?
I can follow up with you offline. I guess I would be interested in that process. There may be some additional diagnostics that would be interesting to save, like what volume of snow is it actually predicting is being redistributed into the leads, and the amount of snow road and stuff like that. But we can chat offline on that.
That would be great. Yeah, if you have thoughts on some additional diagnostics or ways to look at the solutions, we would love that input. So yeah, let's chat.
So I see, Rudra, that you have the question in the chat. Did you want to ask that out loud, or?
Yeah, I was just wondering. I was having a conversation with my friend who's working with Liz Maroon, and they're working with hindcast experiments. And I just got curious that are we planning any hindcast experiments with sea ice to improve the predictability or like multi-decadal predictability of stuff affecting sea ice loss? I'm just curious.
Right. So certainly like the Earth System Prediction Working Group has been doing a lot of forced hindcast experiments with the Japanese reanalysis, and so that's definitely a big part of the Earth System Prediction Working Group. And then I think in the MOM development, as we go forward, we're wanting to test sea ice ocean configurations with the Japanese reanalysis there as well, to try to make sure we're testing the coupling between the sea ice and the ocean. However, we've always done, as a part of every sort of CMIP, the so-called OMIP hindcast experiments that we've had, each time around, and we'll continue to do this. I think this is a useful thing for testing sea ice ocean coupling and predictability, as you say.
Yeah, and if people aren't aware, there's a whole set of initialized prediction simulations that are available. There's a decadal prediction large ensemble, and the Earth System Prediction Working Group is doing shorter timescale predictions as well. And often these are initialized with our hindcast runs, and those are also available. So so like the runs that Liz Maruna is working with, are probably coupled ice ocean hindcasts. So there is a sea ice part of that. Sometimes our sea ice doesn't look great in the hindcast experiments. It can be too thin. And so there can be mean biases in our hindcasts, which can be a challenge in terms of looking at Arctic or Antarctic questions. But I think it would be great if more people were looking at those runs in terms of the sea ice and the Arctic climate.
Yeah,
hopefully
yeah.
will get improved.
Yeah, that answers my question. I was more thinking about like how the sea ice thickness is like always a question of debate, like whether we are capturing that right or not. I think the newer models are doing a great job, but I was just thinking that if there's an experiment of like running a hindcast on seeing how it actually does, I'm not sure. I still have to read what hindcast exactly is. I thought it's a fancy term and I want to know more about it.
Yeah, so we have a standard atmospheric forcing that's based on JRA 55, the Japanese reanalysis that we use to drive an ocean sea ice coupled model.
Okay.
That's what we refer to as a hindcast. So it's the atmospheric forcing looks very much like what was observed over the historical record because it's using a reanalysis product and it's forcing. Yeah.
Got it. Yep. Thank you.
Yep, and happy to chat more if you would like to look at those and want to find those runs. I mean, some of these runs are, most of these runs are available. So for people to analyze. Well, is there anything else? I see we're losing people and we had a great set of talks today. So I expect everybody needs a break from Zoom. So if there's nothing further, so we'll have more of a discussion tomorrow, and please join us at 8:30 Mountain Time, and we'll have another nice set of talks and then some discussion, yeah. So thanks everyone, and see you tomorrow morning.
Thank you.